Let's get started then. You can see my presentation.
Yep.
Yeah. So, welcome to the second meeting of the study group. My name is Hashmaps to tell you. I'm a digital community champion or ambassador for the Algorand Foundation. Go on to the next page. So, welcome. Study group, yes. So we have a Discord. It can be like the primary discussion place is on Discord, the official Algorand Foundation Discord, or the Algorand Community Discord server, and you can find us under the cryptography study group channel. For anyone who wants to join us, there's also a GitHub repository I'm using to organize information and resources surrounding each with each topic. So first, please introduce yourselves. Jacopo.
Hello, so I'm Jacopo, and just a computer science student, and I'm here to learn and see, just like the other time.
Yeah. Great. So the topic for today, after a discussion on Discord, was L1. It's called Layer 1s, Layer 2s, and alternative blockchains. So this is the agenda. So we're gonna just quickly talk about what is a Layer 1, and then talk quickly about like so-called alternative blockchains, and then go to Layer 2 solutions, which I think is like, I'm gonna try to be fast with these first two sections, because I think that's not as interesting as the Layer 2 solution part. And then also the final part is going to be about Algorand, and not specifically, but like, there's different points regarding Algorand and in the context of Layer 2s. So first of all, the anatomy of a Layer 1. A Layer 1 is a network of nodes, and they share this block assembly and validation software, where each block is composed of a number of transactions. And they have a networking layer. Now we're kind of using the layer a lot, but like the nodes are in a network with each other, and they propagate the blocks among each other, and they propagate individual transactions as well. And they share a common blockchain history. And there's a consensus mechanism involved, so you have to choose. Someone can only have. We want like a straight line of blocks a straight chain of blocks, and so we need to choose someone who's going to have the privilege of adding their block to the chain or appending it to the chain, and the how of that is decided by the consensus mechanism. So you can use proof of stake or proof of work or proof of time and space, and there are all kinds of mechanisms out there. And then depending on the consensus mechanism you choose, but also what kind of hardware requirements you want to accept, you're gonna have different properties of the blockchains, and including the block speed and how fast finality will be reached after how many blocks and what it means. And so there's a security model you have to consider here. So it's not enough to just add a block to the chain. You also have to make sure that blockchain can't be reverted, or a malicious actor can't revert the chain or can't add bad illegal transactions into a block. And so every L1 has its so-called security model, and you can look at how easy is it for various actors to collude, how decentralized is the network, and where hopefully by making it more decentralized, it's going to be more difficult for a single malicious adversary to take over. Because at least if you have multiple malicious adversaries, they might be malicious in an orthogonal way to each other, and so like they won't be able to. They're not going to be kind of like working together to do their malicious activity. And then we can also look at the cost of corrupt, like how much does that actually cost to corrupt the blockchain or to ruin it. And for proof of stake, this is going to be a function of the stake of the market cap, because a malicious adversary will need to buy stake. For proof of work, it's going to be a cost of, we have to look at, how much energy and hardware is being thrown at the network. And yeah, there's another way of looking at a blockchain also as to think of it like as a world computer, as like a very, very slow computer that's decentralized across the world. And it's especially when we look at smart contracts and so-called virtual machines. So the Ethereum virtual machine for Ethereum, or Algorand virtual machine for Algorand. We kind of seeing it as like one big computer that's just like executing the code in many places. And of course, there's a question like, why do we need, like why aren't L1s enough? Like, why do we need more? And yeah, that's kind of the point of this entire talk. So let's move on to the next section. Warning, like I'm going to be throwing out some definitions throughout this whole presentation, and yeah, don't see me as some kind of absolute expert or authority, I should say, because yeah, this is just my understanding of things, and yeah, depending on who you talk to and what kind of marketing they want to do or whatever, or what kind of understanding they've reached, they might use a different definition. But yeah, and yeah, Jacobo, if you don't agree with me, please feel free to jump in. Or
sure. Well, we're going to stick the Algorand way for definitions, for block finality at least.
Yeah,
because I know there's many that.
Yeah, that's true. Block finality. Yeah, that's one of those terms that definitely get abused.
Yeah, well, actually, I want to say one thing more, if I want. Yeah. If you
we talk.
Sure. About the. To imagine blockchains like abstraction, computer abstraction, or like the computer in the sky. Like you said it the same way that Tim Roughgarden said it also. I don't know if you listened to his lecture or two, but he made a point. Tim Roughgarden.
Tim Roughgarden.
Tim Roughgarden. I'd like to be able to be more precise on who he's, like a professor from. I saw some lectures from him on the A16Z crypto channel, like but to cut directly to what he said is that actually blockchains are what cloud computing wanted to be in a certain way, because you can actually. Tell a difference when you say like there's an abstract computer in the, like you cannot actually pinpoint where it is, while in cloud computing right now you say, okay, it's in the sky. It's like you don't actually have your own server, your own computer in the server room, like but you use what is in, like, I don't know, whatever Google or AWS or everyone else is like positioning their own servers. While in blockchain, you can actually tell that it's a cloud computer, like something in the sky, because you cannot pinpoint the position of every node of the entire network. So, yeah, I think it's very cool to utilize blockchains this way, like,
exactly,
cloud computing.
Yeah, actually, yeah, like I actually haven't included that, but you definitely, like, there are networks, like blockchain networks, that are basically trying to replace something like AWS.
Yeah, I think ICP.
And the token is being used to pay for it, or were you paying for the hardware using?
Mm-hmm. Oh, okay. Oh, so you
like more explicitly, like, of course, yeah, they are all computers, or like world computers, whatever you want to call them. But of course, yeah, you can expand. Like here we have like very limited opcodes in a virtual machine, whereas you could have.
One example I think it's very similar to what AWS is ICP, because it's very it's not I think ICP is more a competitor to AWS than to layer one blockchains, because it uses data centers as basically nodes, validators. So it's not as decentralized as you want to, but it can support basically traffic like an AWS data center. So
thanks for bringing it up. Another aspect to it is also, like, when we look at zero-knowledge proofs, and we won't really cover them that much. We'll like mention them a little bit in this presentation, but a lot of them, from what I understand, like, they seem to have been kind of like, from what I understand, I might be wrong here, but like when they came out, like if you're looking at research from the 90s or something, like a lot of them were kind of thinking of like, well, we have a bunch of computers that are very slow, or we have computers that are slow, and then like, what if we can use knowledge proof to kind of to compress computation, and then but then these computers just more slow, and they just became stronger, and then it kind of lost interest, like it wasn't as relevant, and then now of course we ended up with slow computers in the form of blockchains, and so kind of brought this the whole zero knowledge proof stuff back to life, or at least the computation compression aspect of it. So yeah, so the first thing just to mention is code chains, and I feel like code chains is like something we talk a lot about in Algorand context. I don't know how much it's talked about elsewhere, but I've also heard something called like app chains. I'm not sure if it's the exact same, but the idea is that, well, already have, let's say, Algorand, right? Well, for whatever reason, you might want to run your own version. Like maybe, maybe you're a country and you're gonna run your own CBDC, so something like that. But then you just want to use Algorand, but you want to be in full control of the token and all of these things and the nodes and
more like a permission version.
Exactly. Yeah, I'll come to that. I actually mentioned it here. That's a good point. Okay. Permission. Or you look at a collection of, let's say, shipping companies or like logistics companies, and you want to have some kind of a blockchain for logistics, or your So then you just want to. So then we can talk about code chains, and the reason why we talk about code chains a lot is in Algorand is because there's this question of like, well, what if? Well, first of all, so just to say, like, so the point is that a code chain separate copy paste of a blockchain, of an established blockchain, and as everything owned and independent, could be permissioned, could be non-permissioned. There's this idea of licensing. So Algorand has a license actually that's owned by the Inc. And it basically is a very permissive license, but it's basically saying like, if you want to run your own permissioned, like if you want to run a blockchain that's open to the world, then you need to also show the source code for that blockchain. Like you can't, because they want.
So you cannot make it fully private. So
or like you can't, or like if you want, then you have to buy a license from them, so then they can make money off of that. So if you're on a CBDC or like a supply chain conglomerate or maybe some industry who want to run a blockchain together, then you can get licensing for that. Otherwise, you have to show the source code. And the idea is that you don't want to have, or like Algorand, like additions are being added to Algorand all the time, is being developed, and then if someone else comes to the code chain, it would be nice for those, if there's some innovations on that code chain, to also be able to come back with the Algorand blockchain. And for interoperability, you just need like a normal two-way bridge, however you want to implement.
Can it implement state proof since it's still EVM?
Exactly. So that's the idea, that state proofs. And if you do a code chain of Algorand, then you're obviously gonna get all the state proofs and all of those nice things.
Well, I think you can imagine easily, like for the usage of a code chain, you also can tweak around the consensus, because if it's permissioned, you don't need to have any sort of maybe not even algo. You can just have everything in euro and use it to spam transaction however you like, and then post like the result every 2 weeks on the Algorand blockchain on the mainnet. I mean, so you can you can have interoperability between your code chain and the mainnet.
You can have. I mean, you could do all kinds of stuff. Like you might, if you're a country, maybe you don't care about running very small, like maybe you would want everyone, like all the node runners, to have super massive like computers running. Then you could have like 10x
you can
transactions, TPS.
I was wondering, because I know that AVM is able to distribute since you only have to hold the algo in your wallet to set up the participation node, but if you make like a code chain with no stake required, so you can basically just say, okay, I know X, Y, Z validators, and they are spamming transaction between each other, so I don't need any of them to reach consensus through traditional stake method. They just know each other and they post transaction. But maybe I want some level of security in case I want a certain validator to be able to to actually validate transaction more often. For example, I have 10 validators. I want like the one in Rome. Okay, imagine in Italy, I have validators in like main cities, and I want the one in Rome to be able to be like a fallback in case some other validators work not perfectly. And can I maybe just tweak the consensus around and have some sort of proportionality? Like I don't know how to.
Yeah. So what you can do, I mean, definitely like there are things to consider. So for example, you could definitely consider like this case where you have, instead of having algo the token as being what determines how as being the stake, right? You could have like a citizenship, right? So if you're a citizen, then you're allowed to run a node for your country, right? So then you can contribute to the decentralized security of your country, which I think that's like politically, I like that's what I would like think, or that's kind of how
I think that would be easy. Wouldn't that? Well, if you make it permissionless, I think that will be an attack vector for Sybil attack. I mean, you can just have other people use their identity to set up a node and just use more.
I mean, at least like you. So
yeah. Well, who's attacking. So yeah.
But with a Sybil attack, then you can't, because I mean, sure, if you have, is it like 60 million people in Italy? Yeah, like if you have. But at least like that's the limit. Like you can't, like a Sybil attack is like where you have many kind of unlimited amounts of masquerading. So at least you have one person, one vote, kind of like a democracy, right? And so at least like every person can only have one of this citizen token that's used for consensus. And then maybe you want to use euro for other, for paying for transactions. Like you can have this dual token model, and then you could also give companies their own like one vote, right? And then maybe ministries or departments like 1,000 votes or something. So you can kind of play around with this model
where
tweak, right? Because especially so this is especially, I think about this a lot, because when we look at, for example, in Sweden, we have this something called Swish, which is like Cash App or Venmo in the US, and it's basically replacing. I mean, besides using card, you use this to transfer money, and it's basically like replacing cash. And so, but then you're reliant on this, I don't know, a handful of banking companies, like banks, that are providing liquidity for the system. And so, like we're seeing more and more where the case where basic functions of like, so transacting, right, in a society, that's like a basic foundation of society, right? And you don't want to put all that power in the hands of companies that are, run by private, like they're run to provide to provide profit for their stakeholders, which is, that's the entire point. And so maybe we will see, like we're seeing a lot of these things. For example, there was a school app in Sweden, like that was basically like for children, like for parents of children, so they could get information about their kids from the school. And so the government commissioned this consulting company to create this platform, and it was just so bad. It was even like leaking private information. So you had these parents who were developers who hacked together their own application that was using the APIs that the school platform was exposing, right? And so you had these citizens coming in,
do it your own,
stepping in for the government. And so when the private, so it's a lot of things you could look here, and I think like that's a super interesting discussion, and I think about that a lot in terms of when we think about politics and how blockchain, like governance and like where our countries are heading when everything is becoming more and more digitalized, but still, like how can we create digital societies that are also kind of open and democratic without giving all the power to. But let's move on, and I think a lot of these things might be covered by, like, a lot of these ideas that we're bringing up are covered like in different terms. So for example, sidechain, which is the next one. So there's another term being thrown around. So the idea is that you do have a separated independent network of nodes, meaning that they have their own security considerations, like for how these nodes could be corrupted, stuff like that. But the goal is to assist an L1 from the side. And so they like the validators are kind of paying attention to the parent chain. And the example I have here is the Milkomeda C1. So it's a Cardano EVM sidechain. They're providing EVM capabilities to Cardano. And so there's this wrapped token, wrapped ADA, or Cardano token. They have a Milkomeda bridge. I don't know the details about the bridge, and I don't know if it's like a multi-sig, like
how it works.
When we're talking a lot, I have to mention this now because I'm not sure like if I have a good place in my presentation where I talk about this, but when it comes to all of these solutions, and when you have interoperability between chains, layers, you have to really think about even if like I'll be talking about some advantages you'll be getting or that they provide, you have to always think about the vulnerabilities that come from moving assets across two different networks. And so in this case, I don't want to.
I read something about Milkomeda. They were working similar to the optimistic rollup, though, because they also talk about the A1 as a rollup.
That's different. I'll come to that.
Okay.
I'll come to that later. That's a great point, though. So A1, there's also an Algorand EVM rollup for Algorand. So that's a rollup. This is a side chain.
It's a rollup, okay.
And I don't. Yeah, we'll talk about the difference between them. But I think they're quite similar. They're calling them different things, and I think they might have to do with the way, like what you can do with Cardano versus what you can do with Algorand.
Okay.
But we'll come to that point later. So the sidechain has its own EVM, built-in EVM, so you can create Solidity contracts and post them to the sidechain, and then pay for them using this wrapped ADA. And you can call them. You can call these contracts. You can call these contracts using transactions on Cardano. And it kind of pays attention and then triggers them, and then But regarding the details of the Milkomeda bridge, I don't know the details. It could be good, could be bad. I don't want to say anything. I'm not like. I just want to mention them because now this just happened to be my first example. But I just want to highlight that these bridges, you have to also look into how they work. Now we have oracles. So the idea is that there are some truth. So within the chain, we have truth. Like we have truth. Like we have truth in the sense of that we have accounts, we have state. We have balances, right? And we can decide on, like, we can reach consensus on those things and how that will evolve across blocks as people transact. But then there's also like what's happening off chain, and the goal here is to plug in some kind of off-chain truth, into like information from outside the chain into the chain. And when we so one way to do it would just to be like you could have a contract, let's say like what's a truth? It could be like a sports game, like the results of a football game, and then you want to have a betting contract on chain, but then you need to know who won or who lost the game. And then depending on that, the smart contract will execute. And you could just have like one person, kind of like a trusted person saying, oh, well, this team won. But that's difficult. Like it's not good to rely on that, because they could just bet on this team losing. And then even if they won, they can just lie and say, oh, they lost. And then take away, like steal all the money. And so we have to create a decentralized network of nodes. And then we have to incentivize them to tell the truth. And then, that's how we end up back in the blockchain world. I call this Ask the Audience from, do you want to be a billionaire? So for example, Goracle servicing Algorand, right? So they have a token actually, but it's an ASA on Algorand called Gora. And they have these contracts. One of them is called the main contract, where the nodes will stake their tokens and then they will register the public keys. And then consumers will request data and they will send this kind of subscription action to the chain, to the contract. And then off chain, what's happening off chain? Well, the nodes will be living. So the individuals running Goracle nodes, which they can do in return for money or like a reward. They will pull the main contract for requests to see if consumers are requesting data, and then they will prepare the data in a block, and then there's some kind of proof of inspired by Oracle. Inspired by Algorand, this pure proof of stake sortition using verified random functions and all these things to decide on who gets to post the data. And then votes for the block are tallied, and the data aggregated if it's depending on what kind of data it is. Like you can combine different data into one and then present it to the consumer. And then, so the summary is that nodes do exist. They have their own nodes, but the token and state is kept on chain. And then we have bridge networks. So they're very, very similar to oracles in the sense that you're reporting activity outside of the chain into the chain or some truth. And here, the specific case here is specific like chain activity. And actually, Goracle, I think they also provide something similar. So that's why like these definitions that I'm throwing around, like they're not set in stone. And people, maybe some bridge networks are oracles as well. But typically when we have a bridge network, you could say, so there's a deposit box contract on chain A, and then meaning that, let's say it's a contract on Algorand, or let's say it's a contract on Ethereum, and then what you can do is you would dump ETH into the contract. And then the idea is that on a separate contract on Algorand, you can withdraw a token as a result called wrapped Ethereum. And so you can bring your Ethereum into Algorand. And because you've locked them up on the other side of the chain, on the other chain. And then you need some kind of messaging service to communicate, and you need this bridge network then to ensure that what happened in the withdrawal box, in the deposit box on the other chain gets told to the contract that handles the withdrawals, right? So how do you prove that you have deposited money? And then you rely on this decentralized network of nodes. And so we have examples. We have Portal, Wormhole. Wormhole is I have here italicized here decentralized, because there are some bridge networks that you can definitely debate how decentralized they are. We know like Wormhole is very powerful. It's a very popular solution for bridging or sending messages across blockchains. And we know, for example, that Messina 1, last I checked, they're using it. I think Messina is a bridge in Sicily, right? That's like where the name comes from.
Yeah, the bridge is missing in Sicily.
Yeah.
They want to build it from like 20 years. But...
Oh, they haven't built it yet. Okay.
Yeah, it's so basically a meme.
It's supposed to be, yeah. So Wormhole, Wormhole is composed of these 19 Guardian nodes, and these Guardian nodes are like very, very strong, like heavy duty nodes, but there are only 19 of them, and so you have to and they're all like, I think they're tied. Some of them are like tied to Solana. Some of the Solana VCs are running them, I think. I don't know, but so but it's very popular and trusted by many. Then there's also Flare Network. They also do some Oracle stuff, but they have you can run your own node with Flare and contribute to this to the decentralization of these, and then get rewarded if you're telling the truth, or if everyone agrees that you're telling the truth, and then and be punished if you're not. So this is better than having a so-called multi-sig. I call this multi-sig, which is where you might have 5 people who all they designed with their own keys, and then that's the truth. But then of course the question is there a better way? And here's where we come back to state proofs and that solution.
Actually, sorry, I just thought about the thing, but do you cover also Polygon within the layer 2s after? I don't want to otherwise say
a little bit, but
okay.
If not, then you feel free to bring it up later.
Just a question about it, because I know it has a multi-signature, and it's a side chain. or because it's a bit confusing for me how I just looked a bit at how Polygon works, but I know that there's a multi-sig. I know that there's like you bridge from layer 1 to the side chain. It's not actually layer 2. It's more like a side chain.
Yeah.
So,
yeah, I know also. Was it Arbitrum? Was it Justin Bonds who was talking about Arbitrum, or was it one of these layer 2s that were also where the kind of contract was also relying on multi-sig? And so to give an example, like there was this. Let me just Google first before I talk too much. But there was this bridge contract that had 9 multi-sig, and then they got hacked. I'm trying to find which contract hack. It's called, what's it called? Raven? No, it was something.
Ronin.
No. What? Yeah, Ronin. Was it Ronin, right?
Yeah.
They had, was it like, I think they had like 9.
Yeah, there's one, I think one of the biggest.
The Ronin bridge. Yeah, it was like a huge, they have like hundreds of millions or something. I mean, in the middle of the crypto,
Yeah.
It was everything, so people throwing so much money into it. But yeah, they had like a bridge into this separate application-specific chain for their game, right? And then I think they had 9 people, like 5 out of 9 had to sign, and then I think some of them were like from the same company, and then so they all kind of got hacked in one swoop.
Yeah.
And then
I think maybe I remember. I don't want to be confused. I think it was because one of the accounts, one was managing one of the accounts, was applying for a job, and then from that job he got hacked through a PDF file that was hiding an basically virus, and he was able then to crawl back to his account to the key, and was more. I actually don't want to say too much because I'm not sure it was this like one but there was one hack that happened this way.
Yeah, it's like so that thing where you have like this kind of multi-sig solution. And so when I say is there a better way, well, the better way, and that's where Algorand is heading to, is, well, what if the chain itself, like what if the nodes on the chain give a proof, so-called state proof, of what's happening on the chain, right? So instead of having like chain A and chain B talking to this middleman, this bridge network, then what if, because here, like, you could have, let's say that both of these are proof of stake networks, and let's say chain A has a market cap of like $10 billion, and then this other also $10 billion. But then let's say that this bridge network, it only has a market cap of, let's say, 100 million, right, or $10 million, right? Like you have a token, and then so then an attacker, if people are relying, people might have a lot of faith in the smart contract on chain A. And a smart contract on chain B, because they're backed by these nodes that are, with very small likelihood, going to be malicious, or malicious activity is not going to be tolerated, or it's going to win out, right? But then the bridge network might itself be susceptible. Like it might be much cheaper to attack it, and then you could cause some havoc, right? Put this bridge. So then the idea is that, well, what if the chain A? It's like, what if the chain A itself is creating these? The validators on chain A are creating like a small proof, a compact proof, or a certificate of what's going on chain A, and then chain B is also doing the same, and then smart contract on chain B can read from that proof and then be convinced in some way, or you're running some kind of light node that's tracking all the activity in chain A and updating its own state. So that's what state proofs are all about. And so state proofs are out, but then now they're looking at the Algorand Inc. people, researchers are looking at how to so-called snarkify it, how to make it easier,
easily verifiable.
Yeah. So instead of providing this compact certificate or state proof to chain B, you would be providing a proof saying, I know of a compact certificate, right? And then I can prove to you that I know of it. I'm not going to show you it, but I can prove that I know of one that, proves that X activity happened.
But one thing I was wondering, but so this ZK-SNARK will be able to make Ethereum able to verify a state proof, right? So the main goal is to make it easily verifiable for more for less performance chain.
Yeah.
Or is it like for every chain? Because if state, for example, like, I don't know, Solana, I think it could, or something like some other chain that maybe are able to
I mean, like,
more.
I mean, we're saying when we say, or this is not me saying that they're snarkifying, this is what they have said themselves. We're just snarkifying the state proof, they're turning it into ZK-SNARK, or making it easier to create a ZK-SNARK. And I don't know the details about that. I do know that there are certain, so basically, like, there are certain computations that are easy to make with a normal computer that are difficult to do in a circuit that is used to create a ZK-SNARK. That is difficult. Yeah, I don't want to go into details because it's really outside of the scope of this presentation. But it's a bit tied to the previous talk we had, which was about elliptic curve cryptography and pairing stuff, and like finite fields and stuff like that, and like kind of computations you can do there. And so they're doing stuff that's gonna make it easier to create a ZK-SNARK, and that's ZK-SNARK. Of course, is gonna be, let's say it's a growth 16 ZK-SNARK. I don't know what's gonna be, but maybe they'll create as something like that, and then maybe there's gonna be this one trusted setup, but it's gonna include all of the nodes on Algorand for that circuit. And then they're just gonna continue like producing these ZK-SNARK versions of the state proof. That if it's a growth, if it's growth 16, I mean that's easy. Like Ethereum has ways to verify, right? Like the EVM can verify growth 16 ZK-SNARKs, and I'm sure, or I don't know the details, but I wouldn't be surprised if Solana can do it as well. So it's not, the idea isn't just to create something for Ethereum, but we do have
so it's generally.
We do have the London Bridge, right? This company who are working on it, on creating this bridge, this smart contract for Ethereum that's going to be able to verify these state proofs. And it's not just about verifying state proof, but like maintaining a light node that keeps track of the Algorand state and then updating itself regularly. Oops, sorry. So looking at the next thing, I'm talking about like layer zeros. So this is idea of chain of chains approach. Maybe, I have these examples, but the idea is that you're gonna like you could have kind of central chain, a relay chain, or and then you have these other peripheral chains happening. So, for example, Polkadot, you have the relay chain, and you have these pair chains that are all bidding for slots to add to the relay chain or to participate in that. And Avalanche also. I don't know if it's. I mean, Cosmos is very typical. Like they're very. That's their pitch, right? Cosmos. And then, but Avalanche, they have these. It's a bit. I'm not an expert on these chains, and I'm still a little bit confused by Avalanche. But they have these. The primary network subnet, which itself is contained of the C chain, the X chain, and the P chain, and then they also have like custom subnets you can run. But so the idea is that let's have a bunch of chains, like layer 1 chains, and then our chain will be the one that's in the middle. And actually, if Algorand could make the state proof stuff work, it could also become the layer 2.
Layer 0,
chains, right? If there's some way, to interoperate, like if you want to move from Ethereum to another chain, maybe you would go through Algorand to do it. Or if you have these co-chain, like let's say you have...
Or co-chains, I think co-chain will more look closely to what Cosmos is doing.
Exactly. Like, okay, so let's say you have country of Germany with their Algorand co-chain, and then country of Australia. And so and then maybe the two countries are going to have like a centralized bridge because they want to control it, but maybe they would just go through Algorand. And here I want to make something. I also want to bring a topic because people always ask like, okay, so what's the point of like, why would I buy Algo and participate in Algorand, this blockchain, if like people like okay, so like why would I do that if anyone else can just run on Algorand co-chain, right? Or like what if country X adopts this CBDC with Algorand blockchain? Like how does that help? Sorry, with the Algorand node software, like how would that help Algorand mainnet? And so, I mean, first of all, it would be like a huge validation for the Algorand software, right? That a country would pick it for their activities. But the second reason is that Algorand main chain is a decentralized network, right? It's like a permissionless, it's open. Of course, like the market cap goes up and down. and recently it's been going down, and which has implications for security. But it's still like the most decentralized version. Like if a country creates their own code chain, like that's gonna be associated with that country, right? And so Algorand is always gonna be the neutral chain, like the main chain of Algorand, the mainnet of Algorand is gonna be the neutral chain. That if you're if you're two different code chains talking, like maybe they would prefer to go through the Algorand main chain, just because then they can be they can be sure that there is a permissionless network of decentralized nodes that are going to be inspecting the state proofs that they're going to be providing and verifying, honestly that this looks good or this doesn't look good, rather than going through like directly, like two code chains talking directly. There could be something like that. Like, I mean, we'll see. I just wanted to mention it. It's called layer 2s. And Algorand also, layer 0s. And also, like, another thing I want to mention, that Algorand has a very, very fast finality, like instant finality. And then now we're going down to like 3.3 second block time. So if you're looking at, like if let's say you want to do atomic swaps, like it's a project that I'm very interested in, specifically with Monero, but could be like, Algorand and Bitcoin or, whatever. Maybe if you like, rather than doing atomic swaps between Bitcoin and, I don't know, Cardano or something, I don't know, directly, maybe you could do it through Algorand, just because the tools might already be in Algorand, and also because Algorand's already so fast, like the transactions, like you might be adding 7 seconds addition to your overhead from using Algorand. So we'll see how that develops. But yeah, so I just want to mention that like Algorand could be this layer 0 as well. Yep. So channels, right? So channels, they are bidirectional. And so let's say Jakob and I, we want to create a channel. What we would do is we would lock up funds in a multi-sig contract. So we would both provide our public keys, and then in this contract, and then fund it, and then it would be set up. And what we could do then is off-chain is we can create transactions and sign them without actually posting them to the blockchain itself. And so I could have a transaction that says, oh, I'm gonna, out of these funds, allocate this much to Jacopo, and then I can send it to Jacopo, and then he can choose if he wants to post it to the blockchain or not, or he can just wait. And then maybe Jacopo wants to do the other way around. He wants to send me money, like allocate more money to me, and then he could send that, you can send a transaction and send it to me, and then I also have the choice there. And you can create additional logic around that, because it's a smart contract. Maybe the transaction is gonna be, maybe the contract can have different types of transactions. So for example, it could be it could be a final up-to-date settlement transaction. It could be like different logic surrounding the channel. This transaction is only gonna be valid after, maybe I'll send a transaction that's only gonna be valid after a day or 2 days. And so Jacopo can't claim it immediately, which will allow us to kind of keep talking or keep negotiating maybe, or and then if maybe I might come up with a more a different transaction later, and or before that's going to be valid before then, and then that one can be settled. So and this, by the way, this doesn't require a multi contract. It can also have a contract. It could also be like a UTXO, unspent transaction that's being sent back and forth on the blockchain, and that's actually how Lightning Network works. And like these, so like I said, it's like a ledger of IOUs, that we're sending back and forth, and the channels, like, they're payment channels, and then there are state channels. So state channels, the transactions aren't just money back and forth, or money, it could also be like storing state, like, oh well, storing this variable, incrementing this counter, like stuff like that. But Bitcoin Lightning Network, it's a payment channel, and it's a network of these of bidirectional payment channel. So the idea is that the idea is like this. Okay, so because it's because a channel, because it is a layer 2 solution, and because we can send transactions to each other off chain, like there's really like no limit, right? Like to how like we're not limited by the blockchain and the number of transactions we can send to each other, but we're still between us two, right? So what we can do is we can have a network. Like let's say we are 1,000 different people, and we all have channels to each other, or portions of the network of these people have channels to each other. And so maybe I want to send to Jacobo, but I don't have money to Jacobo, but I don't have a channel set up with Jacobo. But maybe Jacobo has set up a channel with Alice, and then maybe Alice has with Bob, and then maybe I have set up a channel with Bob. So what I can do is I could talk to Bob about sending money like to Bob, and then Bob will will in this IOU ledger set up a similar of the same amount that he's kind of owing, saying I'm gonna owe this to you, Alice, and then Alice is gonna do the same to Jacobo. And then that way, instead of sending money directly to Jacobo, I'm sending it kind of indirectly through this network.
Does it require like an atomic transaction to go through all the routing, or you just rely on each?
So that's the question, like how you would do it. But yeah, I think you could definitely like have. There are ways of doing this where maybe like, oh, if this transaction goes through, then you can spend this transaction. And so yeah, that's how you would ensure that it goes through. I don't know the details of how they're doing this on the Lightning Network, but
I didn't understand. So if you close it, you're secure that it went through? No. What did you say? Like,
so the thing is, like, you don't like, you can just have it open, like you can, because like I can send you a signed transaction that's going to be valid soon. Like you can spend it soon, and then that means that I will be owing you, right? But then there's like more logic. So how to put this? Like when the channel is open, we both of us like we can be sending signed transaction to each other, and you can create kind of these time limits to them. Like, well, this can only be spent after this time or within this time. And so, I mean, eventually, like the channel is gonna close, but you can decide on like when, like using the time limit that's left. You can also choose if you want to close the channel beforehand, like before you reach the maximum time limit. And you and I can cooperatively do it. We can agree, or if we don't agree, like there are some punishments that can be included. It's called uncooperative closing. Actually, if you want, we can check the Lightning Network Wikipedia page. Or like, does this make sense? Maybe I'm not, I don't think I'm explaining this in a good way. Or
for the uncooperative closing, or if you say for the.
So let me just share. Wait. I'm not sharing my screen, right? Let me share a different window. Now I'm sharing this.
Yeah,
I can be like super stretched out. Let me fix. I have like a ultra wide screen. Just looking at it, right? Yeah, it's a peer-to-peer system for making micropayments through a network of bidirectional payment channels without delegating custody of funds. Yeah, so you're not delegating to anyone. Yeah, you open up a payment channel by committing a funding transaction, and then a number of Lightning Network transactions that update the tentative distribution of the channel's funds, right? So you just have these channels that are open, and then the excuse me, and then like depending on the latest transaction that I have signed and sent to you, like you and I are gonna owe each other a certain proportion of the money that we have locked up, right? And if I'm passing a transaction through me to you, that you're then gonna, because let's say that a transaction is being routed through us, then that's gonna affect how much, I'm gonna owe you something, and then you're gonna pass that. You're gonna in return also turn to Alice, some other person, then you're gonna become, owe them, right? And then in the end, like all of this will be settled at some point. But yeah, so to set up the payments, the channel must be closed. To initiate this process, one node broadcasts the most up-to-date settlement transaction to the network, and then either when there's a cooperative closure in which both parties confirm a distribution of funds. Distribution and funds are immediately settled, and then there's also this malicious, or like this case where there's not a cooperative closure, and for example, it could be if one node just kind of goes offline or does become fraudulent. So for example, it could be broadcasting an outdated, incorrect distribution. Like let's say it was valid like a day ago. I owed you a bunch of money a day ago, and then but then through you and then later, like through this in our channel, it flipped, right? And then you started owing me stuff, but then you shared the transaction from yesterday where I was owing you all the money, and try to broadcast that. And then there are these there's a dispute period where I can settle that, where I can be like, no, that's wrong, like I don't agree with this, and that's wrong, and I'm gonna share this other transaction that you signed minutes ago that shows that no, that's not true.
So in the case of a double spending also, or no?
Yeah, exactly. It would be like a double spending, sort of like that. Yeah, like you spent yesterday, or like you spent something like after yesterday. Originally, like yesterday, I owed you, and then later you owed me, but then you're trying, to act to broad. Yeah, exactly. It's exactly
So
like double spending.
I didn't understand, but so the dispute period, how does it decide which one is more? Does it like rely on?
That's a good question. It might be enough for me to show that you try to close it with an older transaction, and I can prove to you that you have signed a transaction afterwards that is newer.
So it relies on a timestamp.
Exactly, it does rely time lock, hash time lock, but of course the question is how do you do this on Bitcoin, because Bitcoin isn't that advanced, like it doesn't have this advanced virtual machine.
So I think it relies on its own network and then posts it on Bitcoin. No.
Yeah, but you're using I don't have it here. Where is it? You're still using Bitcoin like unspent transaction logic, where you can decide, and so there's some scripting you can do in the Bitcoin in Bitcoin. Like you can, for example, have hashing, where you can say, well, you can spend this transaction if you can produce the pre-image of this hash, and then you include the hash in the unspent transaction, and then when it's time to spend it, the person can provide that hash, and then you can tie that with also time lock. I'm trying to find. Here's this part is about the routing, and they're saying it's going to look a lot like tier 1 ISPS, like it's going to be like the onion Tor or onion routing technique. Trying to find, where is it? We can always just look at that thing. This is the summary. So here they talk about hash time lock contracts. Yeah, hash time timeline.
Okay. Okay. So this is the
Global state across multiple nodes via hashes. So able to create. Yeah. So you have to be able to create a certain transaction only valid after a certain date using lock time. So that's, I think, an opcode within Bitcoin. And then you also have this part, which is knowing does a participant is responsible for disclosing to the next participant whether they have knowledge of the pre-image R. Yeah, so they all commit to each other then by providing the hashed, taking a value, hashing it, and then that hash is a commitment to the committed to the pre-image, and then at a later point they have to reveal that pre-image. Yeah, like here.
I have a question. So
if Bob,
I was just thinking same to the dispute period. Same question. So if you make a transaction and you close it unilaterally, so we are not both closing the channel, so it's not cooperative. I have a certain amount of period to post the response to dispute it, and afterwards, what happens? So if I post it like after this period, is it gonna to be just dropped? Just like, okay, you have this other hash that says that there was actually another transaction that wasn't included in the closed channel, and in case there's a follow-up to that channel, is everything going to be rolled up? Like what happens to the Nakamoto consensus? Or so that's some yeah, because I'm thinking, what if it's time stamped? Like how much is how much time does the dispute period take into consideration?
It says here, so we're looking at here if Bob can produce. So looking at this here, they agree to the following terms for the hash time. If Bob can produce to Alice an unknown, yeah, if he can produce the pre-image to unknown hash H within 3 days. So 3 days is this limit.
Yeah, okay, 3 days.
So 3 days, which is of course like very, very long, and
yeah,
even for Bitcoin.
Counts for.
It's like, so the contract by paying Bob 0.1. So this here, yeah. So this is like an unsigned transaction that has this logic in it. So trying to find, it was a good picture I saw. Okay, yeah. But yeah, I think this, for people who want to learn more, we focused a lot on these channels. It's not that important to us at details, but the point that you should know is that let me switch. Oops, I hope it's still recording. So the point to know is that channels are bidirectional. That's the point. Like it's set up from person to person. Like it's not. Yeah, they're handled person to person. Does that make sense? Yeah. Or entity to entity. It's bidirectional, and then you need to create this network of entity, like bidirectional connections, channels to settle across like different users. Or yeah, how can you see my presentation now? Like, can you see my PDF?
Yeah, but I can.
Okay, great. But yeah, and then we come to rollups, which are like all the rage. So the basic principle is that, if you have 100 people signing 100 transactions, that's going to require, on the layer 1, that's going to require 100 individual signature checks. But then what if they were all bundled up and presented as like one batch, right? At least, so from the perspective of the layer 1, that would only be one signature check, right? And so what you could do is, let's say that there was a so-called sequencer, or they have different names, sequencer or operator, or rollup node. Or let's just say sequencer. Sorry, not rollup node, but the batcher, right? So there's some entity that's gonna grab a bunch of who's gonna be getting these rollups or these transactions and then batching them up into a rollup and sequencing them one after the other in chronological state. And they're gonna post them to L1, and then just to be like, well, this is the pool. They're posting to L1 like, hey, this is the pool of transactions. This is the batch of transactions for now. And then the validators are gonna see this batch, and they're gonna off-chain. They're gonna validate it, and then if it is valid, then they're gonna post a proof that it's valid. It's gonna say like this. Yeah, these are valid transactions. They can be settled, and that proof L1 can be verified within the L1. So what the point here is that when you have 100 people signing 100 transactions, and you have 100 signature checks, when you're batching them up there, and then these validators for this roll-up network, they will sign that one thing, and then that one thing will be verified within L1. Then when requesting withdrawal, so from the individual, from the perspective of a user engaging in a rollup who has sent, so I haven't mentioned here, that's stupid of me, but like we're talking about here is that when you send a transaction to a rollup sequencer, what you're actually doing is you're locking up your money first of all into a rollup contract, and then from there you can send. So then you enter into this L2, and then from there you can send.
You make every transaction. Yeah,
exactly. And so then you can also then you request a withdrawal. When you request a withdrawal, then you can the user posts a Merkle proof validating that their withdrawal transaction is in this verified. So when you in this batch of transactions here that is roll up, you can verify that it's there, because I'll come back to this later. We're gonna talk about in more detail. We're gonna talk about how this is handled by the Milkomeda A1 Rollup. I'll talk more about that. We'll come back to this.
Yeah, just one question. Does the sequencer have an ability to basically apply math to the operations? Since you can decide the order. I mean, I don't know if you can decide. He just gets the batch of transaction and posts it on
Yeah, I think so. So the point is that there needs to be one node or one entity that is collecting these transactional batch, but probably that sequencer is also doing some kind of validation, right, on that to see that they're not double spending. I think
but I see the validator, since he is going to be the one that posts a transaction. If you, I mean, it's more like a third-party issue because you're relying on the centralized sequencer. What if this sequencer apply math, try to extract value from the order of the transaction?
Oh, you mean extractable value?
Yeah, the minimal
or mining, miner. I think actually, so that's a good question. I think that could be possible. That could be a problem.
Yeah, if you can decide the sequence of the operation, since you're just going to batch more and sequence. But if you can do this job and say, okay, I mean, okay, now we have centralized entity for I don't know rollups, so you rely on them not doing anything. But if you want a fully decentralized sequencer,
yeah. So it would depend on is it one centralized sequencer? Is it a bunch of them, and then they don't know? Is it for example, are they using pure proof of stake to decide on a sequencer?
Yeah, exactly.
Does that sequencer know before?
Well, if it's a proof of stake, you can actually apply math, because if you have most of them, it's not actually it's not stake. But if you
sorry.
If most of them apply math, as soon as someone is picked, you have to the leader sequencer. I don't know if they decide to go this way, but if you have a leader sequencer, as soon as he's picked, it's going to be to apply math to the batch and then extract value from that.
Yeah,
and maybe someone else won't, but since the signature will be valid for every other sequencer, but it's just a different order. So I don't know, or if the order is checked. I don't. That's my question. I don't know if changing the order of the signatures is going to effectively like make the batch malicious or not.
Oh, I don't know if I would assume that they're all being settled kind of once, like that the transaction order, or that's a good like. So the question also like, yeah, like is the timestamp like the transactions are going to have some kind of timestamp, right? And I would assume, I might be wrong, I would assume that they would all have the same timestamp, like all of those. They're going to be settled at once within the L2 rollup in this batch. Like they're all kind of counted. So it's not like if you have three transactions, and then depending on which one got settled first before the others, then that person can make more money.
Yeah, maybe you can include one into the batch.
Yeah,
if you're the sequencer.
And that's a good question. Like it's something to think about, like when you have sequencers and how they get chosen, and do they know beforehand that they're going to get chosen so that they can manipulate stuff?
Yeah, because right now they're centralized, right? From what I understand.
I think, I mean, it would depend on the rollup, but yeah, that's typically, that's a problem with some rollups. So, but actually, it's funny because I was reading. We're gonna come to this later, but there's a blog post, or sorry, a forum post by Vitalik, and I think he was mentioning MEV as like kind of, it's almost like a good thing. Like, well, this is a way for L2s to make money. So
yeah, true. Also, Barnage was making a point about that in the Discord. I remember some time ago. Oh. Yes, there was also a presentation that was sponsored, actually, part of the Algorand Center of Excellence that was talking about Algorand, MEV on Algorand, where the difference of MEV on Algorand versus the MEV on Ethereum is that since you don't have priority on transaction with gas-free market, you just basically have a latency war, but you can apply in a certain way.
Yeah, exactly. Yeah, I get you. Yeah, there's also that aspect, like how much. Yeah, because it's not like if you pay more transaction fee, like the node is gonna get more of that. It's more about which one was first. Yeah, that's a good point. What I mentioned this with types of proof. So there are two main types of rollups: optimistic rollups and ZK rollups. And so, starting with optimistic rollups. So, right. So what the point? Like the point is that we have we have a network of nodes, a group of nodes, who are running the separate, kind of like a separate blockchain, like an L2 blockchain, and then they're relying on the L1 for verifying certain things, like which they're relying on the security of the L1 and some data availability on L1 to run this L2, right? During this symbiotic relationship. And so here we mentioned here that, well, so we have these transactions that are getting batched together, and then they're getting then they need to be, this batch needs to kind of be settled in the sense that within the L2 they have to kind of reach, they have to, each block gets added to, like in a blockchain where you have blocks being added on a, appended to a chain, similar way, these batches, these rollups, these batch transactions, it also be settled in that sense. And in optimistic rollups, what we're doing is we're just assuming that the validators are acting honestly. So when this rollup block gets posted on the blockchain, we kind of just assuming, well, there's nothing wrong here. However, they provide a stake just in case, right? And so you're also going to have these auditor nodes. So there are going to be other nodes on the L1 that are, other entities on the L1 that are going to be looking at these rollup blocks, and it's going to see, well, this rollup block has a fraud in it. Like there's some fraud going on here, and I don't agree with it. Like this doesn't look right, and so I'm gonna create a fraud proof, right? Here's the proof that this is wrong, and then I'm gonna post it in Ethereum, and then that's gonna be provided to the smart contract, and then if it's true that that something is wrong here, if I can prove that this is wrong, then the stake that was provided by these validators or the validator is gonna be forfeit.
Wow.
And yeah, so that's kind of like how can you say? Sorry.
So it's like more okay. Yeah, you do what you want to do. Then if you mistake, like you get it.
Yeah. So yeah, so it's like that, and it saves like let's say that 99% of time, things are going well. Like everyone's acting honestly. Well, then you're gonna save on so much transaction, like so much computation, right? That 99% of the time. But the problem is that when you have this channel time, the time when auditors can provide fraud proofs, you create really long settlement times. So, right, because you want to get adequate time, right? So we mean, like, let's say that you're on L2, you want to take out your money out of the L2 into the L1, so out of the contract, right, to get out your L. You might have to wait. I mean, you have to wait for a week. I think I forgot. Was it Arbit? I forgot which channel. Maybe it's Optimism. It's like this.
Optimism, yes.
Yeah, it's 1 week wait. So that kind of sucks if you.
But does the challenge time always occur, or only when there's like a sort of challenge?
I mean, you always. I think you always need. Don't you always need? You need to always make sure. Like, how would you know when it's?
Yeah, you don't know exactly.
Yeah, you can know beforehand.
So it's a bit worse than what you go from for a Lightning network, right? Because at least Lightning network, you have an approving of the.
Yeah, but the question with the thing with Lightning is that it's like bidirectional. So you do have this network of, you have a bunch of nodes, like a bunch of different channels that have to align, and so I don't know how long that would take, because with settlement.
Oh, okay, sure.
If they're kind of getting staggered, yeah, that's a good question though. I haven't looked that up. How long? Yeah, it takes to get your money out of a Lightning network. But the nice thing about
days, no? I mean, if you account for more swaps, no.
Yeah, we mentioned it was like 3 days.
Okay.
And but then more. But yeah, I don't know how it works when you have multiple channels.
Yeah, if you adapt more more channels, you have to also account for like 3 times 3 times 3 times 3.
Yeah, or addition. Yeah, 3 plus 3 plus.
3 plus, yeah, that's 3 plus.
So the nice thing about optimistic rollups compared to ZK rollups, which we're going to talk later or next, is that they can incorporate many EVM specs. So the optimistic rollup can have like a proper EVM. Like you can post solidity contracts and have them on this rollup, right? So you can have very sophisticated EVM contracts, despite this problem with the settlement times. So ZK rollups, on the other hand, rather than optimistic, it's pessimistic and suspicious. So what's happening is that when these batches are being posted to the L1, right? They're including these zero knowledge proofs to validate, like they're validating that this is true, like this is valid. And the thing about zero knowledge proof, I mean, that sounds great, right? But there's also some other considerations with zero knowledge proof. So you have to think about, is it a trusted setup? Is it not a trusted setup? What's the proving time? What's the verifier time? Stuff like this, right? But you get like very fast finality, because if it's a valid ZKP,
yeah,
right, as long as something wrong hasn't happened, if it's like a trusted setup and then something weird is going on, you can have very fast finality. And yeah, so they're good for rolling up simple transactions, but there's this huge research topic, is how do you translate the EVM opcodes into this rollup? So how can you create a solidity contract that can be verified, like arbitrary solidity contracts that can be turned into, that can be snarkified, right? Or zero knowledge proof. So this is like its own research topic. But this is the future of rollups, and rollups
also like the ZK EVM thing. So
what?
This is where the ZK EVM.
Exactly, okay. ZK EVM. And yeah, so this is it's called the future of rollups, and rollups are considered the future of scaling. So it's kind of where the future is heading on Ethereum. Then we have plasma chain, and plasma chains are very similar to side chains, but they're benefiting. What I want to say is that oftentimes plasma chains they only have one validation node, and then sending stuff off chain and then posting Merkle root state commitments to contract on Ethereum. So the point is that they're not posting everything on the chain. So they are posting, they're keeping the transaction data off chain and only posting this Merkle root state commitment. And yeah, so the rollups, they're posting all of these transactions in the batch to the chain. So they're getting stored on Ethereum, right? And that's a cost. That's a cost that you avoid with Plasma chains. Plasma, but then of course you have to think about the decentralization aspect of this.
Sure, because if they're stored off chain, if someone loses the, exactly. I don't know, if their off chain component gets somewhat attacked.
Yeah, so Plasma chain, they accept fraud proofs, so they also have that problem, with the off chain, with settlement times. Now we have Validium, which are like ZK rollups. So basically, I haven't really explained this really well in this presentation, but Plasma chains and Validiums are kind of like analogs to. So a Plasma chain is like optimistic rollup, and Validium are similar, are like ZK rollups. And both of them are they're not keeping their transaction data on chain. Right. So and Validium has these, they call them data availability managers that need to be kind of making the data available and to prove that, if you want to verify this stuff. And if they, so this is also introducing, a problem, right? Or a security issue or a vulnerability. Interesting, Starkware, they have both. You can run both of their ZK rollup or in ZK rollup mode or in Validium data availability mode. But yeah, I'm mentioning Plasma chain. Basically the L2 solution I've been mentioning now, they're like, if you go to Ethereum and you check the docs, they have they have these 4 listed there. And yeah, there's this blog post. This is what I wanted to. This is what I mentioned before. This Vitalik Buterin forum post, and he's basically mentioning that the Ethereum ecosystem is likely to be the way he's kind of making this. He's kind of saying that, well, the way that the changes updates are coming, basically the big changes, the big benefits are gonna come for rollups, and Ethereum ecosystem is likely to be all in on rollups. Plus some Plasma channels he mentioned.
So they dropped the scaling L1 solution.
Yeah, sort of. Yeah.
So does Danksharding, if I remember correctly, Danksharding was like a way to make cheaper data availability?
Exactly. So that's where I was just about to come to.
Oh, okay.
So instead of providing more space for transactions, Ethereum sharding is going to provide more space for blobs of data, which Ethereum itself does not attempt to interpret. Okay. So verifying a blob simply requires checking that the blob is available, that it can be downloaded from the network. The data space in this blob. I didn't post the rest of that. Wait. Let's actually go to it, just because. Am I opening it in some different? Yeah, I'm opening it like a bunch of these windows. I just let me just.
By the way, I was thinking about the Validium, right?
Yeah.
So if they could use, to solve the off-chain component, if they could use some interoperability bridges for data availability, and then you could use some decentralized network for off-chain. It's not fully off-chain, but it's off another chain. It will be off another chain, not off-chain.
I'm gonna come to that because that's exactly what that tweet. There's a tweet by Sebastien, and we're gonna come to that actually. Wait. Let me check. Oh, sorry. Share screen. I'm trying. Hello, and then let me share my screen again. Where is that window? Yep. So looking at it, yeah, he's looking at this is from 2002. This is from 2020 actually, October, and he's asking what would a rollup-centric Ethereum roadmap look like, and it's basically the roadmap he's saying that they're on. This is the code I took. These facts together means that ecosystem is going to be likely all in on rollups scaling strategy. And talking a little bit about how to make it. Need to work more on cross L2 transfers, because when you have a bunch of L2s, they're I mean, you kind of like, the risk is also that you're kind of moving activity away from the L1, like you make, or like attention, I should say, which and there's just like less stake in the layer one, then it's also going to reduce the
security. Sure.
And you also don't want to all of your liquidity to just be completely
dried up to the L2 layer.
Yeah, and also it's going to be a problem with composability. Like if you have different smart contracts, and then you're going to have to post them to all these different rollups, and then how are they going to be able to talk to each other, or
if only Ethereum was faster, it could be, or if only these layer 2s could be like on Algorand. You could imagine like some sort of aggregator on layer 1 of liquidity, and then every L2 like points to L1. Since you have faster finality on L1, you wouldn't have those problems of withdrawal or interoperability, because it will be like near instant finality. So
we're gonna talk about that later. It's interesting. So here, what I mentioned, like they're kind of mentioning like this MEV, to collect fees / MEV that can fund development. It's kind of saying, well, maybe it's good. And then what was it? Saying. Yeah, so he's talking here a little bit more about a single high security execution shard, right, that everyone possesses, and then it's going to be this data availability layer that's going to be sharded. It's sharded chains for data storage. And is there a way? Proto Danksharding. So there's this idea about Danksharding, which is, I don't know how they came up with that name, but
I don't know. Every time I hear Dank, the only thing I could think of is memes. So
yeah, exactly. Where did I get this quote? I'm trying to find it. Is it exactly? So this is where I got the quote. Sorry. Danksharding is a new design. Main difference is that instead of providing more space for transactions, Ethereum sharding provides more space for blocks of data. Verifying it, that the blob is available, that it can be downloaded from the network, and this space is expected to be used by layer 2 rollup protocols to support high throughput transactions. Merge fee markets. So this is definitely interesting for us to think about on Algorand, and also when we look at the
data availability layer. Oh wait, a question about rollups. So just because he was mentioning here, maybe a bit the other page, I don't remember, was mentioning about rollups speed. Yes, over there, like rollups can get to up to 3,000 TPS or so. What's the bottleneck for rollups? Like, is it their own architecture? Is it the sequencer? Is it the layer 1 block?
I mean, I guess you have to also look at settlement, or finality.
Okay.
Right? But also, that's I guess if you look at optimistic rollup, where it's basically it looks like you can run your own EVM, right? But I'm sure you're gonna get the same thing, right? Like the same problem that you get on the L1.
Yeah, because I was thinking if the L1 gets congested, all these proofs that you have to post are also going to be how can I say? So their throughput is going to be reduced, no? Because if the block is not going to fit the entire proof, you're going to need to either wait for a block to be able to fit it, or pay an even bigger gas fee to have it fit in.
I mean, so that depends, I think, on how they do this data availability stuff. So if they're only including the proof and the proof that they do have the data for it, sort of, if that makes sense. So
Okay.
That we're not actually providing the data, storing the data in the L1, then that might still not, because I think what you're saying is like, well, if everyone was on the L2s, just gonna bring a bunch of, like, if you're just posting the transactions right off, like, isn't this also gonna fill up each block? I mean, you will still be able to fit a lot more transactions than you could on the L1, right? Because you're still only verifying one signature in this, theoretically, on the L1. But I mean, obviously, like, when you're splitting things into different, like, L2s, it also comes, it's not as good as having everything on L1.
Yeah.
Especially because you do get the split, and then that's the question of, like, how are they gonna do across, like composability across L2s and these things. So I don't know, but we'll see. But it does look like they're kind of turning in Ethereum into this kind of L0 layer 0.
Yes, it's going to be an L0 basically, like Avalanche.
An Avalanche out there.
Because the Avalanche has its own, like, how did you call it? I don't remember. C chain, no? P chain, no?
P chain, X chain.
Yeah.
I'm trying. Okay, well, yeah. So this is this interesting thing to look at. Maybe if we prepare differently for this thing, we could have read all this.
I mean, it's very detailed, but it's interesting to see. Like, we can maybe just go on the other topic and keep. But we'll obviously post this on the GitHub, and maybe you can go over it another day.
We can come back to it.
But it's very interesting because I don't know. The more I see it, the more I think it adds problem to solution. So it will be interesting to see what's I don't know. Study more.
It is. We'll see. We'll also see. Like, I mean, we could just get some really, really cool ZK stuff, and then, like, I don't know, like, maybe ZK is going to advance so much, and then instead of having an L2 on Ethereum, you might get, like, a ZK only chain elsewhere, and then maybe that by itself will be fast enough. But but you do like the Ethereum. It does have, like, this huge number of nodes. It does have all this money. Like, they're able to secure, like, one. Like, say they can secure, like, one type of. It's kind of like if Algorand was, like, the only thing it was being used for was to validate ZKPs, like, to do pairing checks, and then that's, like, the only thing it was good for.
And
then everyone is, like, posting these pairing checks to check an AVM. That's, like, the only thing it's really good for, and it's, like, has all this, like, the super high market cap that's just validate keeping the security, and maybe that's, like, kind of the fate of that blockchain. Just a quick comparison table, of these L2 that I mentioned. The Optimistic, Rollup, Plasma, fraud proofs, but then one has, does it have on-chain data or not? And so because they become reliant on these data availability managers to provide the data, and then you have channels. They are no, and everything, but, like, they are. The thing about them is that they are bidirectional. And then we come to this section 4, Algorand. So just, like, talk about, like, what are the pros and cons of Algorand. So just, like, because we're talking about, like, L2s, right? So we have to understand, like, why even care about L2s for Algorand, because we do have really nice properties. We have instant finality, and we have. I wrote soon here, but maybe by the time some people watch this video, it's gonna reach 3.3 already, and 10K TPS. This PPO, pure proof of stake leader selection, and then just various aspects of Algorand just makes it super fast, and the bottleneck lies with networking. And right now, like, running a node, a participation node is easy, like, it's simple for anyone, and then it's just, like, the kind of like a small trade-off in like how in that the relay nodes, like the nice thing about relay nodes, you can just beef them up as big as you can, and then you would get, so then you can you would
you scale the network just by beefing up relays.
Exactly. But still allowing the stake to be run, like normal people can run a node. But of course, like we can come back to talk about the networking. But this also creates, this is kind of like the big top, the big thing. What do you call it? Like how do you need to handle this in a certain way? And they're working on it, on improving the networking aspects of it, and how we can reward relay nodes runners, and how we can make them more.
Yeah. Also, actually, how can we remove relay node, because they're working also on the gossiping network.
And so the question is, where can L2 come in? So the thing about Algorand isn't like Ethereum. Ethereum has, you pay gas, and then you can just have, from what I understand, you can just have like, as big of a contract, and then just as much as you can pay, right? But Algorand isn't like that. Algorand has like, they're saying, well, this is how fast, this is your budget. And if you can't fit what you want to do in this budget, well, too bad. And because, the chain is fast, it's going to have this block time we're aiming for. And so it kind of creates this upper limit on the smart contracts you can run. They're still very powerful. And especially now when we have bulk storage, it means that you can do, what you can do is you can, or in some cases, in many cases, what it allows you to do is you can split up your computation. So let's say that you would want to do some crazy big long computation, but maybe you could split it up, right? So you can do some part in this block, and then the next block it will continue to the next computation. So for example, ring signatures, where you are validating individual signatures in a ring. So maybe you want to include like 1,000 signatures in this ring signature. And then like you can't fit all of that into one block, but maybe because you can modularize it, maybe you could allow the whole thing to take place over like 10 blocks or 15 blocks. And then that way, after 15 blocks, it will have finished. And then in the meanwhile, the people who want to, they will have made their simple transactions, right? Like just like payment transactions. They won't have been bothered by your long contract execution, delaying everything. But there's different things to think about: the opcode budget, like the opcode smart contracts, and also application specific L2s. Like if you know that you're gonna need a lot of space or a lot of and then maybe you don't want to do this. Maybe you don't want to share with everyone else. Maybe you want to create your own Algorand chain or code chain. And like I mentioned, the real improvements, like we're talking now proofs and codes, like I don't think it's at least for me, I mean it is nice with smart, like it would be nice. I mean I understand like there's a lot of focus on like, for example, creating EVM. So now we do have the Milkomeda A1, like this EVM compatible, right? So it's really great that people can come with their own, they can just copy lift and shift contracts. That is nice, but
no, but also because I think there's a lot of like interoperability pros, but also cons to what Algorand can provide, because you bring in EVM contracts, but they're going to be executed at a EVM level without the actually like the power, the power that you want Algorand. That you come to Algorand because you want the fast finality, the throughput in 3.3 seconds. But if you start then relying on a sidechain that has EVM, actually Milkomeda has like what's the throughput of Milkomeda?
I don't know. They have some calculations on their page. We can take a look at it actually later. But that's the question. Like they talk about epoch, and like they have like 6 blocks, I think, where you get to post your batch. Like if you're a sequencer, you get 6 blocks to just post like these batches. Okay. Because the thing is, like, we're gonna come to it later, but they created everything that they basically created the A1 before block storage, and so they're reliant on transaction node storage, which you limited like to one kilobyte in your transaction node, and then you can have like 16 transactions in a group, so you get like 16 kilobyte, and
So they can just upgrade the. Oh, it's going to be required.
Yeah, so we'll see how they make use of block storage. Yeah, so.
Oh, that's interesting, because also it was talking about block storage for data availability.
Yeah. But yeah, so my point is just like, for me at least, the real improvement rate really not like, that's where the real focus should be, and I'm not as concerned with L2s. There is this line of research from Inc. And so, because back in 2020, Silvio, he had this blog post where he wrote our two-tier architecture, and if you Google it, you're gonna find it. And he talked about, we're gonna have L1, we're gonna have L2 for contracts, right? Because we don't want to delay the L1 by running long block, chains, whatever. Sorry, smart contract executions. And then it was like not any. I don't know what kind of. I don't think I even remember seeing any information after that about the L2s. But then I stumbled upon this this talk by Victor Luchanko, who works at the Inc. And this interview, he's talking about speculative smart contracts in the Algorand blockchain, where he talks about this L2 yeah. So I'll come to that, just what it was about. I think these two are supposed to be like flipped. So yeah, the problem is, of course, accommodating data intensive and computation intensive esoteric contracts on the L1. So data intensive, they can be. Like, what I'm thinking here is, I'm thinking like, okay, let's say you want to have a smart contract and you want to verify, like let's say you want to run an image recognition. Like you want to run that. Like, let's say you want to, Jacobo, if you, I think we talked about this maybe before, but the previous one. But like let's say I have a picture of a cat. Or something like that. Like, let's say, if this picture of a cat if this picture has a cat in it, then give me money or something like that. Like let's say we have that kind of smart contract, like where it's smart contract is verifying if a picture has a cat. And obviously, this is like running this kind of AI algorithm is like incredibly expensive. You could never do this in a normal blockchain. And so it's data intensive, very large image, or to say it's a video, right? And then it's also computation intensive, and just long, right? So the idea then is you would separate. Once again, let me go to this blog post, and I wish I knew how to switch between windows. I'm sharing my screen, but let me just open up so you can see like. You hear me?
Yes, now I can hear you. I lost you for a second.
Just want to double check.
Is it still recording?
Yeah, it is still recording.
Okay.
Single window. Yeah, this is the one I want to show.
Let's go.
So
actually, I see a lot of people confused when they're presenting, like external reviewers always mention this this paper from Silvio. Because they say, Algorand has this two-layer architecture where on the second layer you have contracts, but it's actually not
exactly.
It's been changed. Yeah.
So So first, let me just go through this. So they're talking about why would you want layer 2 off-chain contracts? Content may be too big, computational demanding. You're talking about ZK-SNARKs, and and maybe too complex. So we can come back to the ZK-SNARK stuff a bit later. I mean, but on-chain versus off-chain. So the idea here is that you can see that normal Algorand execution, right? They have layer 1 smart contracts. So, right, where the idea here is that, trying to find, right. So here you would have these transactions, and then you have a contract call afterwards, just saying. And then I think here, like, it's supposed to be kind of like a different size. I mean, sex, like it's not going to be the same length. But what they're saying is, like, what if we have contract calls that are off-chain that aren't tied to the cadence of the L1? That's kind of like what the advantage of it. You can kind of take however long you want, and then you just include it in the block. And then, hurrah, yeah. So it's look here. I like this. This is really good, interesting presentation, actually.
Yeah, I also saw it, I think, last year when it was published. I think that many of the problems he was accounting for the application of the solution have been almost solved. I think this maybe.
Yeah. I mean, honestly, like some of the things you're talking about, like, for example, look, Goracle, they're also talking about allowing for general execution, right? And then you just have an L1, like you have these nodes that are running proof of stake with the Agrotoken, and then they get told, can you execute this
off-chain
contract off-chain, and then they verify, and then all the Goracle nodes, they kind of check each other, and if someone is doing something, but they kind of see. And then the big thing, though, that they're talking about in this, so they're talking. So okay, so they're talking here, the speculative part is that. So what if I'm on the L1 and then I make a transaction, or I make a call to a contract that's off-chain, send all of my money. If this happens, send all of my money to this account, and then while the contract is executing, I then on the L1, while the contract is on L2, then I send my money on L1 somewhere else, right? So then the execution is gonna finish on off-chain.
Yeah, and double spread.
Come back, and it's gonna be like, so what do you do then? How do you handle it? And the interesting theory, they're saying, well, okay, if that happens, then it just doesn't matter. It's just gonna fail when we try to execute it, and then that's fine. You're just gonna have to accept that that's a possibility. But that's what they're saying about speculative, like kind of speculating that it's gonna be possible to finalize that effect of the transaction, what they're calling it. And they just have a lot of stuff. I recommend everyone to watch this. You're saying here, like, in real life, you have a personal check that can bounce, right? So don't write checks that are gonna exceed your balance.
The solution is basically just look at.
So they're talking about some stuff.
Maybe later there's the part I want to go over. No, sorry, just I don't want to interrupt you. Go.
Okay. So here they're talking about, well, what's going to happen is that these contract execution committees are gonna execute the contracts, and they're gonna get a result, and then they're gonna certify them, and then what you're gonna do is you're gonna use. They had this certification they call it, so certificate. You're gonna certificate, and what they're talking about here is talking about compact certificates, and then this was before they changed name to state proofs.
Oh, okay.
So the idea is that you create so what a compact certificate is basically a way of basically you have a bunch of people signing off on something. They're saying this happened. I witnessed this thing happen, okay? And so I'm going to sign off that I did witness that thing happening. And then a compact certificate is basically a way where it's basically this data structure that have combined all these certificates into just one certificate. All the signatures into one certificate, and then in a very compact way, like they get represented in a very compact way, and you can very quickly verify that X amount of people signed this certificate, or this certificate represents X amount of people, or X% of stake, right? And so similarly, what you're saying here is that off-chain, you're gonna run a bunch of, your contract's gonna get executed off chain, and then you're gonna the effect of that, like you're gonna batch together, like not just the effects of your contract execution, but also other people's, and then we're gonna put it into one. You're gonna set people, people are gonna sign off on that, and then they're gonna sign off on this bigger compact certificate of all these things, and then that is gonna be brought down into layer one, and it's gonna be verified using the AVM. And here's the thing. So they're talking about specifically, they're going to verify the certificates. They're not going to verify, of course, the executions, because the idea is that you could do stuff that you can't do on AVM. You're going to do it off chain. But here's the thing, like here's what's interesting, because if they could, like what they could do is what they could, because they are, part of, they are the ink. Maybe they could look into expanding, like in a way that, like maybe it won't be possible to verify compact certificates in the AVM, like in a smart contract. But they might be able to add this feature so that it can exist in the node software, if that makes sense. Like it doesn't exist as a smart contract feature, but it exists in the node software, so that the L2 is really tied to the L1 on a node software layer level. Does that make sense?
I'm not sure. No, I don't understand.
So if you think of like every
node,
node,
going to be like relying. It's like simulate, because it's going to rely on just on the endpoint and not on the AVM execution.
Yeah. So this is what I'm unsure about. But the idea is that so you can either execute stuff like you can add stuff in a smart contract that's going to be verified by the layer ones, right, within each block, right? And they're gonna verify it, validate the block, and that's going to be part of the cadence of the blockchain. And but it might be the case that they might say, well, we believe so strongly in the L2, your nodes should be verifying the compact certificates of the L2 because
within the L1, like the node itself it's both like a node for the layer one and the layer two.
Yeah, so we're gonna see about that, like how that's gonna work out. I mean, it might be the case that what they're talking about here is actually they're talking about snarkifying the compact certificate, and then we're gonna maybe using Groth 16, and then we're gonna use pairing checks in the AVM that's gonna come, and then we can validate. Maybe that's what they're talking about here. I'm not sure. They could also just be talking about like, well, nodes can generate certificates. Maybe they also gonna have ability to like on the Golang level, like because the Algorand software is written in Golang.
But the problem with that wouldn't be that you're relying on the node you're using, because, for example, if I use my own node and then I tweak it to be like, yes, accept everything I give you, and then
I get your point. Like how would you?
How would the other nodes be validate?
Or like how would a bunch of nodes be able to kind of collaboratively validate? That compact certificate. Yeah, that's a good question. So that they would have to.
From what I understood, the way they validate is that they just have they just look at the account output. Like you have X. Wait, maybe I'm not sure. You can correct me on this, but I don't know if you have Alice, Bob, Charlotte, and 5 other people participating on this layer 2 contract. You just, once the off-chain contract is computed, you only post the output of the Merkle tree, the Merkle tree, like the accounts, how they are. Sorry, I can't find the words right now. What's the structure of the account, like the
right,
I can find the
exactly. What is the account state?
The account state. Yeah, what's the account state of after the off-chain computation? You don't actually say anything about what happened on the off-chain computation, or actually you just say, I validated this with the proof, and then you say, okay, so after I did this, the result is this one, the result X. Okay. And if the result also accounts for a double spending, it's going to be dropped. I'm sorry, if the result takes in like a double spending, it's going to be dropped. Otherwise, it's going to be validated, right?
Yeah, I get your point. I mean, then the question is, like how can the layer 1 nodes trust?
Start the computation.
And then you still need compact certificates to kind of verify that, well, these nodes all like think that this is what happened, because what you're going to have is you're going to have Alice, maybe Alice called the contract on the layer 1, called the contract called the off-chain contract from the layer 1, and then the off-chain contract is going to come and it's going to settle the result of that, right? So it's going to grab the money from Alice's account, but then you still, to avoid that being abused, you need some kind of way of proving that Alice 1 called it, and then that it was actually a valid execution off-chain, and so you still need a complex certificate. So yeah, there's a lot of questions. There's a lot of questions. I remember I saw that the Inc. they had this job posting for a smart contract researcher who's basically
for the clarity language.
The Inc. What?
Sorry, for the researcher that no, it doesn't.
I think it was for the entire L2 thing, like just to work on it. And then I don't know if they hired the person or not. I think they did. And then I don't know. We haven't really heard more. And
yeah, I actually was interested about this. I think I tried to post some question about it. So I hope maybe next time there's an interview with John or some actually from maybe Gary from the Inc. where he gets in some answers.
Exactly. I think I remember, and this is kind of, I think we can end this. I remember or have this memory of them talking about like the AVM. Like the thing about this is that the AVM has ended up being just super fast. Like they basically just been able to make all this progress with the AVM. That so, for example,
so it's not going to be useful to have off-chain. It's going to be so powerful.
Yeah, it might not, because, for example, talking about ZK-SNARKs, right? But then if we're now able to verify with this new AVM, with the update, that was what I was trying to point I'm making here. L1 has been able to grow very well, no recent update. So yeah, because with the new AVM EC math PR that hasn't been merged, but it's there. And that was the topic of the previous meeting that we had. Then they will definitely, they were able to validate ZK-SNARKs, at least some of them, pairing based one. So maybe they'd just be surprised at how fast they've been able to develop this thing, or the progress they've been able to make. And so, but we'll see. I still think I think, and also, like I said, like we're also seeing, for example, Oracle networks like Goracle, or I think also Flare, and they're they could also be bringing in this kind of capability. And then it might be a question of like, okay, well, how much better can we make it with our solution, and then how much? But we'll see. Like, we'll see. I would love to hear more from Victor and the other people.
Oh, by the way, here's what I was trying to mention first, the clarity language.
Yeah, clarity language, exactly. So that's the thing, they're talking about clarity language being, so for people who have been in Algorand like a couple of years now, or at least 2 years, like, so Teal obviously has been there from the start, or from the start of the smart contract stuff for logic signatures. But then there was also like Reach, of course, Reach people know about, was funded, I think, by a grant, and then and then there was this third language I was also talked about, was Clarity, which is used, I think it's used in Stacks, which is it's basically this attempt, or it's a solution that allows for smart contracts for Bitcoin in some way. And then so you're programming it in Clarity. And so they also want to use Clarity, or a variant of Clarity, they said, for these L2. And the reason why is because Clarity is like decidable and predictable. I have this in quotation marks, but yeah, it's just easy. Like it's interpreted, and it's actually not compiled in anything else, and it's apparently like this is like part of like formal verification and stuff like that, like where you can predict how the contract is going to execute and stuff. Like it has that property, and so it's like super safe. So that's why they were looking into it. What else to say about that? I don't know.
No, by the way, I was very interested in what you were saying about Goracle. So basically, Goracle will be the architecture of what they wanted to do with the speculative smart contracts, because it's going to be a layer 2, because actually, it's not really a layer 2, but it's like a batch of nodes that run pure proof of stake, and they can run off-chain computation on their own nodes and then post it on the chain. So I think they could use Goracle for that.
Yeah,
or the other way around. Goracle could use this
exactly.
to
I mean,
develop
if you have
blockchain.
enough, if you have enough if they have enough Goracle nodes running,
Mhm.
so it's very decentralized, and
Yeah.
because basically you're relying, so you're getting the security from the L1, which is Algorand, and then you have Goracle, which is a bridge Oracle network, and I know they also like talk about. I mean, they're running on this PPOS proof of stake stuff, but I'm trying to. Then you can definitely get what we're talking here about L2, and I know that I talked to Abdul. Oh wait, let me share the. Let me share
Give
the.
us the sauce.
Sorry, what?
I was trying to meme. Give us the sauce.
Oh, yeah,
Show us.
I know they had that idea of like looking at general executions. Let's see, what am I sharing now? Sharing the right thing. Yes.
Yes, Goracle does.
So let's see, do they have it still? Available feeds, unless they've changed it. They might have removed it. So they have talked about data feeds for, so they have price, sports, weather, which I think weather is going to be super interesting. So crop insurance contract, I think, is going to be really, really big. I think it's like a really interesting application, especially in the global south.
But how would that work? You can
Exactly. So you would have so crop insurance is basically this idea that, well, I'm a farmer, and one type of crop insurance is about price. Like, let's say this year everyone had like super high harvest, and so we're all kind of flooding the market with tomatoes, and so the price of tomatoes is going down. And then now, I can't make, I'm not going to make any money because so then what you could have crop insurance there is that an insurance that's going to prop you up. And then the opposite, of course, is like when you don't get rain. Like, let's say you're very reliant on rain. Like, let's say there's a drought, and then so you can't, like,
so you need to testify that it didn't rain.
Exactly. And so, I mean, crop insurance exists in Europe. Like, we have lots of this crop insurance in the US, but the problem is, like, what about poorer countries, global south, countries in, I don't know if people say countries in Africa, but countries where they're very reliant on rainfall, and where if they don't get enough rain, they don't have enough crops, and if they don't have enough crops, they don't have money, and they're basically devastated. They're basically living like year by year, harvest by harvest. And typically, what ends up happening is that they have to leave their farm, so they have to maybe sell it off, or they have to go into town. They could become this kind of migrant worker, and so they lose this big property just because of 1 year of bad harvest. So then if we could offer them, okay, so then the problem is, like, why can't they have crop insurance now? Well, maybe because, this is because maybe they're living in, I mean, the idea is that they're living in a country where the judicial system isn't trustworthy. Like, you can't set up these kind of contracts because you can't trust the judicial system to adequately compensate you, to not be bribed by the insurance company, all these things. Or there might not be liquidity there. So the idea is that, well, maybe you could engage on the blockchain, in an insurance contract, like with average Joes like us in Europe or something, right? Where we're the people on the other side kind of providing this. So they're paying, like, let's say, every day or something, they're paying like into this insurance contract, and then depending on the weather, however you want to set it up, like the last, like maybe you're accumulating, like you're counting every day, like you're counting how much rain came, right? How much rain in centimeters, and then what was the temperature. So you're storing this in some kind of box storage, and then at the end of the year, you can say, well, it wasn't, this happened, so it wasn't good enough, and so, well, I lost, you win, farmer, and so, well, you take the money, kind of, which is good. Then they get the money, they can survive for another year, and then they don't have to, sell their farm. So,
sure, that would be interesting.
Yeah, so I'm super excited about this one. It's like, for me, because this is what blockchain is about. Like, I'm not interested in trading and stuff like that. I'm not a big trader, but this is what
real applications of
like outsourcing law into a blockchain.
Yeah, that could be also included in what Agrotoken could do.
Agrotoken
is a bit different. It's different because they just validate that you farmed a certain amount of crop, and then you get the value of that crop.
Exactly. So Agrotoken, Agrotoken is about, yes. So when you sell, like if you're a farmer, you just, yeah, exactly. You just sell you just tokenize your crops, and then yeah, like you can sell them directly through that, or you to some kind of warehouse, and then basically like, yeah, we can take a look into that as well, or maybe we can take that into some, I guess, like a different.
Sure. I was interested because Agrotoken is one of the main use cases that I like about Algorand, aside from like ZK-Pay. ZK-Pay, actually, I love it because it's the one thing that I also want to try. Like, I think that should be built. Like,
yeah. So financial assets, right? And yeah, I mean, ZK-Pay is interesting also because I don't think they got a grant or anything. I think they just like independently.
Yeah, they developed. I think they got the grant afterwards. I think that once
they just picked Algorand because they thought it was the best, and then.
Yeah, exactly. That's great because it shows why you need to have such technology, because at some point there's going to be a use case that's going to pick your chain because of the tech, because it needs it.
Exactly. So here you can see that they're talking about the grain-backed stablecoin, Agrotoken, which you can yeah, if you use collateralized using money, then you're highly centralized, you're tied to banks. Liquidation of assets can be time-consuming, highly regulated. Yeah, so I mean, selling, if your assets are in grains and then you have to sell them, or all these things, you're reliant on that. You can add time. Whereas if you're using the grains themselves as collateral, it's really what you're talking about. Yeah, frequently related gold as a store of value. That's the main things that characteristic over time in relation to other assets. This is what's interesting also, because grain have like shelf life, right? Like you farm something and then it needs to be eaten, like, or it's difficult to store it, or even if you freeze it, it's gonna lose value. So, but you're also making it like more what do you call it, like fungible, like your grain, by converting it into this, because there's gonna be some warehouse somewhere that's gonna maintain levels of grain, and they're gonna sell them off, right? And you're always gonna have this kind of fresh grain coming in all the time into this warehouse.
It's also a good hedge against the currency in your country, maybe if like in South America.
And that's super interesting, like also with blockchain in general, where like you want to hedge your bets, right? So maybe for your finance person, like you need to hedge your bets. You need to hedge your investment so that it's not it's very, what do you call it in English, not decentralized, whatever, you know what I'm talking about. So and it's interesting because like maybe you have some kind of derivative off of a grain value, and you can, I'm sure it exists already, but you can do it on blockchain, right? So if you think that it's going to be a good harvest, and then maybe the price is going to go down, like it's going to be good weather this year, so it's going to affect the price of grains this way. Well, and then maybe that's going to hurt me somewhere else. Oh, did someone join? Or Agrotoken is super interesting. I recommend people to read their white paper. It's like a nice white paper. It's easy. We're talking about different things. Going back, so just the feeds. We also have flight, which is interesting, like flight insurance. I think it's super simple. It's going to be super simple to set up, because this is very very available data.
What if it's like a canceled flight? I think that's great.
It's like delayed. Like it's delayed, or flights that, like, let's say like you're on your way to the airport, and then you're like, might as well, like, why don't I, just in case? And then maybe, and the thing is, because it's so cheap, right, to engage in a contract on Algorand, and then maybe you can get a very very low fee, and then maybe like just like simple, it's kind of like betting or whatever, not betting, but speculation.
No, I was also thinking that maybe I don't think if company also wants this, because surely on a consumer side this would be extremely a better experience, but whenever there's like a flight cancellation or something like a very big delay, there's going to be like some contractual problem, because you paid for a flight on a certain day, a certain time, and then maybe you have to fly like 3 hours later, and they say that happened because maybe we overbooked the flight and you're getting moved. So if you have something that accounts for these occasions, like automatically, maybe I don't know, something like that's happen, and the smart contract just automatically reimburse you the ticket, like pay you back, or maybe just automatically check if something like this can happen. I don't know if a company would implement it, because maybe they do actually make money off of this. They they always overbook flights because they account for people canceling or people, I don't know, delaying taking another flight. But that will surely on a consumer side be extremely improvement on the experience, because as soon as there's a problem, okay, you get what you should get. You don't have to make any sort of litigation with
exactly. And you say the thing is, like, because it's on the blockchain, and because you're avoiding, you're essentially able to avoid all this manual labor that could be part. You know, you can also, so basically the point is that you can get in places where there is weak rule of law, you can you can outsource to the blockchain, and even in places where there's strong rule of law, there's like a space of contracts that you and I, like, we can't engage in right now, because it's just like they're too expensive in reality, you know, with current systems to engage in. So it's not really worth our time to engage in that kind of insurance. But maybe if blockchain, because it's so cheap, and you can have, like, you know, tokenized, you can have like 100 people, like, suddenly they want to engage a little bit, you know, insurance. You can add to it, so you can get like this really interesting effects. So like microfinance stuff, and these micro contracts that otherwise wouldn't be economically viable. So I just want to mention this custom data feeds. We're talking about how you could have custom endpoints as well. So here they're talking about endpoints that don't have API keys, and they're working on this. So obviously, like here, like definitely, like what they could expand is they could look into, maybe I heard something about WebAssembly, something like that, or I'm thinking maybe like a Docker container or Docker image, like I think that would be
like on front end on no,
like a like a contract where it's like, oh well, pull down this Docker image,
and
then from Docker Hub, run it with this input, and then it's gonna provide either true or false, and then give me that result into Algorand blockchain, like give it as a data feed. You know, then you could have something very custom, right? And as long as you're willing to pay, you know, the Goracle, maybe as long as you're willing to pay people to have that kind of contract, you know, because then you could definitely have what I mentioned before, the example with an image recognizer, or you could have ChatGPT. I think that's also something that they've been looking into. OpenString.
Yeah, right? That's very interesting.
Of course, ChatGPT. I mean, you have to be careful, but
computation-wise, I think it's going to be.
So let's stop presenting. Let's go back to
Algorand.
Yes, Algorand. So after this L2 research thing, the next topic is Milkomeda EVM Rollup. So I just want to explain a little bit. So the thing about it is that it's not a side chain, because there's like more, because the Cardano one is a side chain, because it's like more stuff happening off chain, like on the separate chain. This is like everything, like this is more, you know, a rollup inside of, you know, Algorand. However, they're still like a little bit early. So sorry, I should mention. I call it AVM rollup. It should be EVM.
AVM.
Milkomeda A1. Sorry. Milkomeda A1. It brings EVM to Algorand. So you wrap algo into malgo you use your bridge to kind of bridge into the contract, the rollup contract, and then you get malgo in this rollup world. And the thing is, it's still in development. So even the docs are a little bit like they're talking about like potential future stuff that they could do, or that's not like how they're doing it now. And so it was difficult to find up-to-date information. Maybe I should reach out to them personally. I don't know. But so they're not using Boxword yet, but they want to use it. And they're using the combined transaction nodes of 16 transactions in a group. So, and then that way you can combine all of them to get this,
16 kilobit.
16 kilobyte, And so they have these phases, right? So first they have a batch proposal phase. So sequencer divides a batch of transactions into groups. So you have a bunch of group transaction and divides it into groups. And then each group, they create a Merkle root, like a Merkle tree for the batch, and you keep the Merkle root. You post it on chain, and then when you post it on chain, when the sequencer posts it on chain, it declares that basically it initiates the block proposal phase. Or sorry, it declares that it is a block proposal, and then it goes to the next phase, which is the batch availability phase. So with the Merkle root on chain in block 0, so you have the sequencer, then you have the rollup nodes, or node validators, you can call them, and they see this, and then within six blocks after this, all of the batch data must be posted. So basically, what they do is they create the groupings that we mentioned here. They post the groups, and also a Merkle proof. So a Merkle proof is just like a path, right? A path within this tree of hashes. Are you familiar with Merkle proofs and Merkle trees?
Yeah.
Yeah. I'm not surprised, because it's used everywhere in blockchain.
Yeah.
If a new block proposal, yeah. So once this person who has been the sequencer has declared a block proposal, no one else can propose another block proposal. Like it'll just be ignored by the nodes. And also, if the sequencer fails to post all of the transactions within 6 blocks, because they have, everyone can check, the node validators can check that all the data has been posted, because they have Merkle root, and then they will check, like, well, did you kind of explore all the paths in that tree? And if all the data isn't posted, it'll be considered invalid. And rollup nodes, they observe everything. Yeah, sorry, basically what I just said. And once they have verified everything, they will say that the batch is available. So the batch has been made available, right? Then we enter the batch validation phase. So locally off-chain. So now they're verified that, well, all of the data has been posted. Now it's time to verify or validate that the transactions are actually valid in this batch, in the rollup batch. And here's the thing, that the transactions, can be EVM calls. And so that's the cool thing about this whole thing. It doesn't have to be just AVM or Algorand transactions. It can be some EVM calls. And if they're all valid, then the state of the rollup will advance a step. Otherwise, they won't, and then they will all collectively, the nodes will collectively go back into batch proposal. And also, yeah, the state of this rollup, it's like deterministic, right? So a new node that reads Algorand, is doing catch up on Algorand, on the Algorand blockchain history, it will be able to get into the same state that all the other nodes, the validation nodes, are in. So then the question is, of course, who gets to be the sequencer and who's the validator? And they're all this, like, it's like they're only, there's like one type of validator node, but then they have elections. They call it elections or auctions. So they're all going to auction for slots of blocks at once, right? So we have this block 0, and then we have these 6 blocks, and they exist, across time in slots. And so what you do is you own M-Algo, and you post it as stake in the rollup contract, and then using that, you're going to be allocated slots. So opportunities in each slot, you're going to have the opportunity to sequence the transactions and post them for the other ones to validate. And so, yeah, so the sequencer validator are like the same.
Okay.
Like same nodes, but like different hats at different times. And then they're also relying on VRF, using L1 for randomness seed. So there's like this, basically, there's this randomness value that's like in the block that they can, or this non-deterministic, like this value that you can't predict beforehand. So they use, and it's included in the block, in the Algorand blocks. So they're using that as a seed for their VRF.
Do they produce the VRF themselves, or like how does?
Yeah, the nodes do it.
Okay.
And then the sequencer, if it has done everything right, will get a reward, and if not, will be slashed. and maybe yeah. So just like Algorand, right? It can tolerate 1/3 of the stake being malicious. If more than that is malicious, then it's gonna cause issues because of the Byzantine fault stuff.
Yeah. By the way, what do you think about slashing? I know I don't know if it's too off topic.
I think, yeah. The thing is, like, so then the question is like why don't they use kind of PPOS in the full state? And
yes, yeah.
So,
I think they introduced slashing because it works similarly to optimistic rollups. So you want to
exactly, it's fraud proof kind of.
yeah, fraud proof.
And it's very important also because the thing is that Algorand, there's a problem here, which is that Algorand cannot verify EVM operations. So it's not like in optimistic rollups on Ethereum, where where nodes can verify, they can check that this batch isn't correct because they can run the EVM operations. And this is not like a ZK rollup, right? So it's not like it's like
there's no validity proof.
Yeah, maybe they'll add that. We'll see. I think they definitely have the brains in that team to provide that.
Yeah, like to move from fraud proof to validity proof.
Yeah, so that's.
But do they need like
slashing?
the new EC, like the new pull request about EC math to do that, or no? You can just already do that.
ZK rollup?
Yeah.
Yeah, they will need that. I don't know how else you would be able to verify. And even then, like some of these ZK EVMs, they're like using more advanced stuff, complicated stuff. So you wouldn't be able to verify them. I think, like Plonk stuff. I don't think you can verify that with the new EVM, but we'll see.
Like not even with the new math opcodes.
I'm not sure. Like, I'm not an expert on Plonk, but I don't know how much it relies on pairing checks and if that's enough to be. Maybe, I don't know. But I mean, there are other stuff like there are other ZK stuff that definitely like are not based off of pairing checks, and I'm not sure if there's enough opcode budget to verify them. Like bulletproofs, for example. But the point is that the slashing. I mean, the idea is that slashing is the downside with slashing is that you have to lock up your algos or your stake, right? So, for example, for Algorand, we don't want. It's nice to not have to lock up your stake, like to not have your algos locked up somewhere. You can go in and out. And I think also Goracle, they're talking about not having slashing. They were thinking first about having slashing, but then they decided not to have it. I don't know. Like, I don't mind it in theory.
Because I know that there's a game theory part you have to take in consideration, because yes, you don't lock up, so you get better security of not having to not even rely on a contract. Like you don't even rely, like, maybe it's not like a third party that you have to rely on, but it's not even a contract. So you can just within your account just hold, and that's it. I think that's one of the best thing about Algorand consensus. But at the same time, if you don't have neither slashing nor incentives, I think I don't know if how this works into taking into consideration the consensus.
Yeah, like, so for example, like, how would you? So I think here's the thing: like, if you have a very, very sufficiently decentralized network and the distribution of stake, right, into honest, like the stake is distributed into honest hands, then you don't need, if it's enough, then you don't need to slash, because the bad guys are never going to win, right? They're never going to get a chance because there's always going to be enough honest people. So I think that's the point. Like, it's not a need for it,
Yeah.
Like, but here maybe they're more afraid, right? So then they want, because when you slash dishonest people, then you're removing, then you're actively taking bad stake and giving it into good stake hands, right? So you're making the whole thing better. And so there is that advantage, and I'm sure, like, here, I don't know, like, maybe it would be good to have slashing in the beginning, and then
and then have it removed,
because then you like, oh well, not afraid of bad people because
there's no way you can actually account for distribution of stake within.
True.
Maybe you can have something automatically trigger slashing if there is like a certain amount of stake online. Like if it's under a certain threshold, then slashing can happen. No, I don't know.
Yeah, no, it's a really interesting thing to think about, like how to turn it off and on. And
yeah, because I think that
like
there
if
was
you get like
governance
99%
vote.
of the sorry.
I think wasn't there a governance vote on slashing? Maybe governance slashing.
Yeah, we were voting on it. Like if we should have slashing for governance rewards. And yeah, that does feel like more real. If you can lose money, then you're not gonna.
Well, but actually, I just think that Algorand could implement a sort of slashing. Like it's not slashing itself, but it's more like if Algorand goes into the implementing rewards to participation node to validators, because also this is one point that it's not certain, because actually the optimistic future of Algorand is just like Bitcoin is the one where nodes don't have to be rewarded. Like yes, in Bitcoin you have like miners getting rewarded, but not gossiping nodes being rewarded.
It's different because in Bitcoin you are expending energy.
Yeah,
and
you have, but you don't have anything at stake outside of energy.
True.
So yeah, there was some interesting video that was going over the difference of security within proof of stake and proof of work. I think I like the proof of stake concept more, but yes, it's a trade-off with decentralization, because at the start you need to have some sort of way of distributing the stake to make it decentralized and secure. But at the same point, like the point of having the stake being the validator and not the electricity is that if an attacker has enough power to use like a country cooled like between many how can I say parentheses, I don't know, not a parenthesis, like whatever. By the way, it could attack Bitcoin because it's used energy for something, and then it utilizes energy also to mine Bitcoin. Like you can divide this power, and once you attack Bitcoin, the energy can be redistributed to something else. While if you attack a network with its stake, once you attacked it and you actually completed your attack, your stake, what you used to attack it, is null, because once you did your attack, you attacked yourself also. So the security of proof of stake, I think, it's a bit better. Actually, it implements a bit of a more dangerous game for the validator, for the attacker. And then, yeah, but Algorand, like if Algorand would implement rewards, it could like slash rewards, like not slash the algo within the wallet, because you cannot do that, but it could like slash the rewards of.
Or you could dilute, like you will dilute. Like if you're giving rewards to honest people, then you're gonna dilute the malicious actors. Of course, you're also going to be diluting everyone else who's not participating in the consensus. But maybe you don't mind that. Like, I mean, we'll see. Like that would also have like very different. That would have some implications. For example, for the for the state model that Algorand has right now with minimum balance requirements, right? Like that would have to be a very dynamic number.
Actually, I just thought you can slash without having lockup. You just implement a way for that an account, when it validates, like it acts maliciously, you basically manually increment its MBR. And you cannot opt out of it. You basically say, okay, you're not stuck with the algo, you cannot move them.
Yeah, everyone's
It's not a slash. No, just sorry.
No, that's an interesting way of slashing as well, or like
you're just blocking that algo, and but it's not a slashing itself, because you're just like not slashing, but you're just saying, okay, now these are just going to be here, and you cannot do anything outside of voting. But it's not slashing because it could still use those algos to vote. So
no, there are different ways of punishing, definitely.
Yeah, but it's good, interesting.
But it's a different thing. Like it's interesting to look at slash. I don't, and also slashing. Of course, if you have slashing, maybe slashing would discourage some people from joining a consensus that might otherwise would have. Maybe if you're malicious, you don't care. Like you're already ready to lose your investment. But if you're honest, like then you might be honest, but still be afraid of getting slashed.
Yeah, like what happened with Ethereum at the start of proof of stake. There was a ton of slashing because of a bug. I don't know if you remember the news, but
I don't remember it.
There was a problem with some blocks, and there was it started a bit of like a slashing all over the place, but it then it adjusted. So yes, like a lot of honest nodes got slashed. So yes, you don't want always slashing, because that's exactly, if you have like honest node runners, they're going to get slashed, and maybe not even without them trying to attack the network.
Yeah, and if by not having slashing, you're getting like, if we're getting double the amount of honest people, I don't know what.
Yeah, exactly. You're still securing. You're incrementing the security, because you're saying you have the algo in your own account, nothing happens with slashing, so just do it. Just
So regarding this Milkomeda stuff, there's a problem. So they highlight it as a problem, and then they're saying like, so first of all, I just want to mention that they're currently running in this so-called basic mode, which is where they're relying on a single centralized sequencer, which does get, so you do allocate slots, and they're talking about like advanced mode, where you would have maybe a pool of operators, they call it, who's like sequencing at a time, I would assume. Also, they had this ongoing problem, like I mentioned, cannot verify, but they're looking into it, of a fraud-proof system. That's more, I guess that would be more than this. It's a little bit, I was a bit confused by the documentation. They do have this optimistic rollup page, but it's still under construction. So so this Milkomeda EVM rollup, I wish them good luck, and let's see where they take it. There's also this ongoing research into block box storage. And then finally, we get to this tweet. There's this tweet. Since let me actually just open it up, because I've been sharing my screen, these pages, all these windows so much today, so I might as well do this as well. And I have to find some way to share, just to learn how to switch windows that I'm sharing. Probably something super simple. I'm just so let's look at this. Sebastien Guillemot. I don't know how to pronounce his name, so I don't want to butcher it.
French.
And he's co-founder of DC-SPARK.io, Milkomeda, working on L2s and ZK and stuff. So definitely also Mina protocol. That's super interesting as well. Recursive snarks. So so they're talking about. He's talking about algorithms adding BLS curves soon. So what he's referring to, I'm assuming, is the ability to verify BLS. Sorry, no, they're adding the EC math opcodes, which includes the BLS, one of them, and you can use it to create so-called KCJ commitments. A KCJ commitment is a type of polynomial commitment. So with a polynomial commitment, so a commitment, I don't know. We talked about this, but a commitment is basically like you're committing to a message, and then you can send that message, or you can send that commitment to someone else without actually revealing the message, and then later on you can reveal what you committed to. Similarly, and then there's no way like for anyone to. The idea is that there's no way for me to commit to something and then change what I committed to, like to trick you in that way. Like it shouldn't be a way. Like once I've committed to it, I can't switch the message, the pre-image, right? Similarly, it should also not be possible from the commitment for if I'm giving my commitment to you, Jacobo, it should be possible for you to be able to figure out what I've committed to. This is like some properties you can have with commitments, unless I want you, or whatever. KZD commitments allows you to do with polynomials, and what you can do with polynomials is you can. Basically, what you can do is, if you think of it like, you can have a bunch of individual values, like let's say points on a curve, and then what you can do is you can say you can create a polynomial that that kind of flow. It has like, let's say you have 10 points, then you can have an 11th order polynomial that goes through these 10 points, right? And so maybe x equals 1, let's say it's a f of x, function of x. At x equals 1 is going to go through the first point. X equals 2 is going to go through the second point, right?
Okay.
And so with a polynomial, you can actually commit to a bunch of values, right? Which is really interesting, right? In one commitment.
Mm-hmm.
And then what you can do is you can also prove, like, the thing about polynomial commitments is you can also you can basically expose what you're committed to, but only at a single value if you want. Like, instead of like providing the entire of course I can provide you the polynomial, and then you can yourself, you have the function, you can evaluate it at whatever point you want, right? But what I can do with these KCG commitments is I can say, well, at this value, I have committed to this thing, and then here's what I've committed to, and like that's the value, and I'm gonna give that to you without actually sharing the polynomial itself. So even though I've committed to like 1,000,000 points, I can choose to only expose one of these points that I've committed to. So just like, and it's very, I mean, this is what's using, I think it's using Groth 16, and it's, in all these different, in various types of ZK contexts is used. And so he talks a lot about this, because I think you can verify KZG commitments using pairing checks. And he's talking about data availability layer. So data availability, he's talking about, data availability sampling. Okay, so what does this mean? It means, with proto Danksharding, we're talking about this, right? Where you want to prove that you have data stored somewhere and that it's still available, right?
Yeah.
And a way that you can do it is kind of like, instead of this, I don't want to, let's say that I have a bunch of data stored. What I can do is I can kind of reveal, you can kind of ask me, well, can you reveal this thing, this random value? And then I can, because you picked it randomly, like, let's say there's like 1,000,000 different things in the storage, and then you pick some random value in this, right? Let's say item 150,071, and then I give that to you, right? I show that storage. The fact that what was the odds of me knowing that you would ask for that item, right? It would be like 1 out of.
Yeah. So the bigger the commitment, the bigger.
But also,
is.
Yeah, it's 1 out of 1,000,000, but also depends on like what is the range of each item. Like, maybe like each item is like a value from 1 to 10, and then in this place, so I have 1,000,000 slots, and then each slot can have a value from 1 to 10, and so so you have this probability, and so you can sample the data and then show that sample to say like, oh well, these random values, I have them, so therefore I probably know all of the things, right? And I can prove to you that this is all like perfectly random. Like, I just picked some random values, and then.
But if you like, is there like a limit to, like, I mean, if someone continuously query the commitment, like, is there a way that you can like sort out the entire data?
That's a good point. Yes, but I assume it would require many.
Yes. I mean, so there is like, there should be like a limit. I don't know, something like.
So then you would have like a huge amount of data.
Yeah, a huge amount of.
Yeah, that's a good point. That's a good question, actually. So he's talking about some stuff. This Twitter thread is it's interesting, and to be honest, I had to read this thread a couple of times to understand. Like,
me too. Once I found it, I was like, okay, save it. I have to read it like 100 times.
So he's talking about state proofs. He's mentioning that so state proofs. So basically, the core of that is that, like, well, what if Algorand could be a data availability layer for other chains, right? So the other chains, they want so they're like, he mentioned like where is it? He's mentioning Celestia, I think it's called.
Yeah, I think so. Yeah,
Celestia, which is also this type of data availability layer for other chains, right? But so Celestia is kind of simple. It's not like Algorand is a fully fledged blockchain, right? It's kind of world computer that I mentioned. And not only, but now with block storage, you can store as much as you want, as long as you have deposit money for it, right? And so you can do more with Algorand, in theory. And so what he's saying is like, and also we have something like state proofs, right? So with state proofs, we can prove stuff from Algorand to the other chain, right? And so I kind of created this step-by-step list of what I think he's saying. And if I'm wrong, I apologize to everyone. And hopefully I'm right in what I think he's saying.
Yeah, I hope he goes over this thing.
Yeah, so can you see my screen now?
Yeah.
So I think this is what he's suggesting, and I hope I'm not misrepresenting what he's saying. But I think he's saying like the following. So, right. So we're getting this EC math upgrades, hopefully coming soon. I don't know what's going to coming, but I think we're all super excited.
I read like AVM 10 after this.
That's great. Yeah, after this. Yeah. And so, right. So there's a problem storing data off chain from another chain and storing it somewhere else, and then verifying that it's still there. That I have, it's that I still have access to it. And so he's saying the following, right? So let's say another chain says I need to store this data. Let's say a batch of transactions, right, for my rollup. So then they bring the data to Algorand and they store it in a box storage, right? And then I can create a off-chain KZG commitment of data in the box storage. So basically creating a commitment to the data in the box storage. And then I can verify. So first of all, I have verified successful inclusion of the box storage transaction. Wait, did I butcher this list? I think this 2 is not supposed to be here. I think I butchered this. So never mind. Ignore. So you store data in box storage from other chain. You wait for the state proof that will verify the successful inclusion of that box storage transaction.
Okay.
And then you take the state proof and then into the other chain. And then the request comes to validate data that's still available, right? So someone asking, well, this data that we stored in Algorand is still there. And then off-chain, we create a KZG commitment of the data in box storage. Okay, so this is not happening instead of Algorand, right? Someone is off the chain, trying to create a commitment of the data in box storage. And then what we do then is wait, did I completely butcher this? Trading data availability. Yeah, exactly. So then this is what I was talking about. I think you can ignore this.
Okay.
And then you can validate the KZG commitment inside of the AVM.
Wait, why state proof? I don't understand. So
the state proof is a way for us to communicate from Algorand to the other chain, right? Because the other chain is gonna tell. The other chain is gonna expect so.
But isn't it always already going to verify that with the KZG commitment? Or no?
Wait. Yes, but no, but okay. So that's a good point. Here's the thing. Let's say that the other chain is kind of. Let's say it doesn't want to verify the KZG commitment. Okay. Like maybe that's too much. Maybe it's enough for Algorand to verify the KZG commitment, to validate it with a pairing check inside the AVM, and then take the state proof into the other chain. I don't know. Maybe this is stupid. Maybe because we're taking a state proof into the other chain, we're taking a snarkified version of the state proof, and so we're already doing a pairing check on the other chain. So I don't know. This is kind of my thoughts about this.
Or maybe it's like a superset.
Yeah. Exactly. Maybe he's talking about two different ideas in parallel, and I try to combine them. But the idea is that you can store data in box storage from the other chain into Algorand, so you can just fill it up.
Okay.
And then, what basically we're saying is that we trust Algorand to store our stuff, right?
Yeah.
And then we have state proof, so we can basically verify that the box storage transaction happened. And I don't know how that
works. The box storage, the KZG commitment. And you get the full check that.
Yeah, maybe
what you
this,
want is there.
yeah, maybe I was right to add this. Maybe I wasn't so dumb.
Okay.
Maybe you need this. So maybe as you store it in the box storage, and from another chain, you do an off-chain KZG commitment of data in box storage. Yeah, sorry.
Okay.
You do a KZG commitment of data in box storage, and then maybe yeah, you would validate this on chain, an Algorand, and then you take the state proof, you send it off to the other chain. It's gonna be happy that, oh well, it looks good. And then sometime later, here's the point. Here's sometime later, because we don't. It's not just at time 0 we want to verify the KZG commitment.
Sure.
Right, that we still have the data. Of course, we have it time 0, but what about sometime later? Like, how do we prove that we didn't delete the data from Algorand? And then to save money or whatever. Well, then that's when you would do data availability sampling. So you would then you would leverage the KZG commitment scheme, validate this, and take the state proof into other chain. Otherwise, I wasn't sure like what he meant, because it's not like we could, because I don't know what else to say, because I don't think it's not like we can use Algorand to generate a KZG commitment, right? We have to do it off chain, and then what we can do it off chain, and then we can ask the nodes to verify that it's valid.
Actually, that's like so. If you want to verify with the nodes, you need to wait 3.3 seconds, right? Or whatever finality Algorand has in the future.
Yeah.
But if you just have to validate that something is in the box storage with the KZG, you can just use the simulate endpoint and have it instantly.
Ah, I see what you mean. Something like, yeah, I don't know how simulate is supposed to be used. If it's supposed to be used for development, if I'm in develop, like if I'm like like let's say I have a contract and I'm doing testing, like integration testing, or kind of like this long bigger testing, and then I want to validate something, or if I can use it for,
because there's a way. Because I saw a tweet from Algorand that was saying, well, you can use simulate to query the chain, because for example, you use the simulate endpoint to try the transaction, or maybe query something, like maybe you can query box storage and say, okay, do you have this? And since you don't have to pay any algo to read the box storage with the simulate endpoint, it's basically instant and free.
Yeah, but I don't. Yeah, I saw that too, but I wasn't sure what she meant entirely, because you can still, I mean, it's like whatever is in box storage is still available to everyone outside of the chain, right? So,
but you need to. Yes, it's already. Yes, it's available. You can read it like off chain, but if you want to read it on chain, you have to pay the.
Exactly, but can my smart contract use simulate? It's on my node, right? Running simulate on my node, and then
okay. And like then you say off chain, like on another chain.
Exactly, off chain. Like kind of like I have my node set up, and then there's like an API, right? This kind of it's like this API that I can query from my Python code running my Algo SDK. I think that's what it was meant to be, but I'm not sure. But maybe she just maybe you're right, and it's like something more to it.
Because that will be very like the best data availability layer, because you can just check data instantaneously.
Yeah, it could also. I think it could also just be a way that's simpler to access the data. It's like this convenient way. Like it's just convenient, but it won't have like. I mean, like you're not going to be able to. I don't see how you'll be able to get, for example, all of the Algorand nodes to validate the case, the pairing check. Without paying the transaction fee, right? Because otherwise you'll be able to spam the transaction.
Yeah, you could spam the thing. Yeah.
So it's interesting to see. Maybe she will also watch this. I don't think so, but it's like super long now.
Yeah, that was something I wanted to understand. Like because from what she said in the tweet, the simulate could do all sorts of stuff. Like if you really can just query the chain this easily, like instantaneously, no fee. I don't know how you can maybe integrate something, but
It makes sense if what you're saying is like it's like an easier way of doing it rather than pinging the indexer or something.
Exactly. You don't need to use the indexer because maybe it's too heavy. You just need to have like some sort of Algorand node, or maybe point to an Algorand node around the simulator, the simulate, and say, hey, I want to check that this box storage has this data, Or no, actually, no, wait. Well, no, you use the simulate to say, okay, so if I run this KZG commitment, do I get this true output from the node?
Yeah, I have to look into that.
Yeah, but it's very interesting. I hope I expand on it. Maybe some question. We could throw some question on Reddit on the forum.
Yeah. But going back to this, so the state, it also depends on like how another chain can read the state proof.
Yeah.
If the other chain doesn't need, for some reason, if whatever reason this other chain doesn't need to snarkify the state proof, then maybe
it could directly read from the state proof itself.
Yeah, then it wouldn't need to do the KZG pairing check.
But would you need the KZG to see if the data is still, because the state proof says that you did the block storage transaction to store it, but it's not going to say that it's still stored, right?
Yeah, I mean, like, exactly. That's the thing. Like, maybe like to check. Yeah, I mean, you could. Maybe it would require like 1 million. Maybe it would require like 100,000 box storage kind of get transactions.
Yeah.
It's for box storage 100,000. But instead of doing it 100,000, you could kind of use a KZG commitment to just get it in one, to get like one single thing that proves that you do have that data availability. I don't know. So definitely, like, he raised some interesting points. I don't quite understand exactly what he meant. I think this is kind of what he was talking about. It's definitely an interesting thing, though, like, because now we have Algorand, we have this
as the data availability,
and maybe that's the only thing it's going to be used for. Like, we don't know how it's going to how the world will be.
It's going to compete. I think that at some point you could make a case that the future of layer ones is going to be like competing for data availability layer.
Could be, definitely. Yeah, I mean, if yeah, exactly. Like, maybe that's how, especially for Ethereum. Yeah, like if the only thing Algorand does is do pairing checks and box storage, used for box storage, and then maybe the L1 nodes themselves, as part of their node software, they're producing these state proofs that are snarkified, and then maybe they've done this kind of, maybe it's a Gross 16, but it's a trusted setup that's been run across thousands of nodes. And so as long as one of them was honest and deleted their tau, like this random value that's part of it, and then the whole thing is like valid. And so now the only thing Algorand is used for is just to do that. It's just for as a block storage. That would be so. Maybe that's where we'll be heading. I don't know. Anyways, what's next? All right. Yeah, I had this point about mixers, just because I had to throw them in.
I was very interested because you mentioned it last.
So this idea, our mixers L2s. So my answer is that they're kind of like a one-shot L2 in the sense that you can kind of get your transaction in once, and then you have to take out your transaction. You can get your funds in once, and then you can make like one transaction with them before you're like exiting. Maybe that's not the definition of L2 at all. Probably not. But so the idea is that make sure you have a smart contract that you would deposit. So the smart contract would be like, so a mixer, right, is used for mixing money for privacy. So you and a bunch of other people are entering your money into a smart contract, and then you can take out that money from another account that you have that has never interacted with your first account, and is doing it in such a way that you can't link which account deposited, and so you can't link the withdrawing account with the depositing account, because it could be like any one of a number of people. And so when you deposit, first of all, you're depositing a fixed chunk of money, because like it doesn't make sense, like if you have like, let's say I deposit 100 algos into this block, this contract, and then you deposit 200 algos, and then when you're doing that, you're providing this kind of proof, either a so-called a commitment or a public key. And so when you want to withdraw, you also need to be able to provide a nullifier or key image. So this is depending if you're using Merkle proofs, large proofs, or if you're using ring signatures to do this mixer contract. But what I want to say is that they have to kind of be like, it has to be fixed. It can't be like you deposit 200, I deposit 100, because then when you withdraw, you're gonna want to withdraw. Then you would have to withdraw 200, and I would have to withdraw 100, and then people could see immediately, oh, you could link by the amounts the depositor from the withdrawer or with the withdrawer. But what you could do is if you have 200, you could deposit 100 and 100, and then I deposit 100, and then you're gonna extract 100 into your other account, and then 100 to a third account, to a second account, right, that you have. So that way you could obfuscate. And so, but what happens is that you get this kind of layers into the wallet. So you have it would have this account-based Algorand wallet, right? So you would have for first account, you would have the keys for it, and then for your second account, you would also have the keys for it. However, you would have this kind of UTXO layer as well, because when you're depositing your fixed chunk of money, let's say that you have 1,000 algos and the contract accepts only 100 algo per deposit, then you would deposit 10 times, and then you would have 10 of these commitment or public keys, and then you could spend. You would have like 10, right? You would have this kind of 10 spends that you can use. So you can. So it's interesting, this idea, like you would require this other wallet type to make, to keep track of these withdrawal proofs. I just wanted to mention that just because you and I, we had a discussion about this.
Yeah.
Just interesting. Yeah. So yeah, finally, like, is there any other thoughts to think about? Do you have any other things?
We talked so much, so my brain, yes, is melting right now.
Like 3 hours now, so
yeah. But it's super interesting. Sorry if I interrupted you many times.
No. It's great to have this be a discussion. I mean, the thought, like, what I really want to stress though is that for me personally, this is me, like, my opinion is that for Algorand, for me, L2s aren't that interesting at this point in time. I think for me, unless it's like oracles, I think oracles are super, but they're not L2s. But oracles are super interesting. But for me, the big point right now is to look at the nodes, the relay nodes, and also how we do archiving. And that's
but that's actually, you raised a point that I want to discuss. But you say that relay nodes are really interesting, but I find more interesting the absence of relay nodes for Algorand. No
absence.
Yes, like if there is a way for Algorand to work without the relay node participation. Oh, actually, no, not the absence itself, but maybe the reduced participation of them inside the networking layer.
So relay nodes are.
Yeah.
So the thing about Algorand is that we have participation nodes, and then we have relay nodes, and then currently relay nodes also act as archiving nodes, and they're also going to have some. They also have some functionality when it comes to state proofs, where they're like kind of helping to accumulate the signatures for the state proofs. So for the compact certificate, right, that we're all signing off on.
Sorry, you wanted to continue?
Yeah, so relay nodes, they have this. So the thing about them is that, so first of all, we mentioned this way before, right? Which is that participation nodes can be allowed, as long as they can they can be allowed to be super small compared to relay nodes, because relay nodes can be as big, as big as possible. And so you get this, you're able to scale basically Algorand in a very interesting way by just beefing up the relay nodes while leaving the participation nodes that are in charge of consensus small. Also, what was I going to say? Also, there's a security aspect, right? Because the participation nodes are not talking to each other. They're only communicating through relay nodes. Or rather, what I'm saying is that because participation node and relay node aren't one, like, if you're doing relay node and participation node with one node type, that it would introduce some security issues. So you have nodes talking to each other, but they're also kind of holding these keys. Whereas now you can create, interfaces. So like, okay, participation node, it keeps these keys that are vital, right?
Yeah.
And then it just kind of talks outwardly in a way, kind of in a very limited manner to a relay node. And then the relay node is very dumb. It's just kind of gossiping.
Yeah.
So that's like
because
the security aspect of that.
No, I was. You also raised another thing that I want to ask about state proofs. But first, yeah, the absence of relay nodes, because I heard Gary talk about this gossiping participation node research that they're doing at the Inc. So basically, both unbeating, if I can say it, like reducing the requirements for relay nodes. Because yes, I think the main critique that you often hear about Algorand is that you have this communication layer that is permission. Like, it's not permission because you have to explain that yeah, it appears permissioned because to access the default participation node, you have to have actually explicit contract or explicit contract with the foundation. But there is a way to run the relay node, because it's just the same software you use for a participation node, but just like a relay type, like a relay mode. And then you just need a bit of more of like connectivity, but speed, because I think it requires like a 1 gigabyte of transaction, not transaction, of gigabyte per second. Recommended at least,
yeah. So it's exactly so. Couple of things.
Also, if you already put those requirements down, like maybe not on the networking side, like not on the communication, like internet speed wise, because maybe that's very important for the gossiping part. But I heard him say these lightweight relays that are not archival, because archival relays are important at the beginning to be a backbone in case of backup for the participation nodes. But if you have enough
archive nodes, they need to be there so that new nodes can read, right? So there are a couple of ways to address. So first of all, yes, we do have we have this we have this participant node talking to relay nodes, and then they are very big relay nodes, and they cost a lot to run, and they have high requirements, and and they also do some stuff, like they do filter out some, like they're doing like optimizations, right? Well, if I already talked to you, if you already told me about this block or this transaction, then I don't need to talk to you again, right? Because you already, or not talk to you again. But yeah, you get the point. Like
you don't.
You are also, you are introducing some logic on the relay nodes that maybe you don't want them to have because they don't have any stake in a sense. However, so regarding so there's something called the phone book, which is this JSON file where you can specify IP addresses of relay nodes. And if you're running your own relay node, of course, your own Algorand private network in, let's say you have Kubernetes running in your own Kubernetes network, cluster, whatever, then you can obviously specify IP addresses for these other relay nodes. And so yes, you can do that now as well. I could set up a relay node, and then you could connect to it.
Yeah, we can have like our own.
Exactly.
But the relay on itself.
Yeah, exactly. But the problem is, like, how can I get that relay node to talk to the other relay nodes?
To the other relay nodes. Yeah. Is it automatic or?
So that's the thing. Like, that's where it's that's where it's gonna get. You're gonna have to see how they. I don't, because there's no like from what I know, like a process to kind of tell these other relay nodes, like, hey, pay attention to my relay node as well. But so we'll see, like. But definitely, like, so archive nodes, they need to be there, because you still need, at least for now. And so let's see what they do with stake proofs. Maybe they could, I think they could do stuff with state proof, like maybe recursive. If they ZK-SNARK the state proofs, and then you get recursive, then maybe you can make recursive state proofs. And so maybe you could like skip from block, let's say like 3. Maybe you would have to do catch up in the beginning blocks of Algorand, but then once you reach the point where state proofs became snarkified,
you just use
all the way to the front, because you can trust, you can do this ZK-SNARK computation and data compression, right? And so you can create a proof that of a series of ZK. You can create a proof that of a series of snarkified state proofs who take us from state X at, let's say, block 30 million, which is where we are right now, and then to block, let's say, 100 million, which we might be in a couple of years, without having to go through those 70 million blocks, because I can prove ZK-SNARK, the magic of ZK-SNARKs. to get there. So there's that aspect of how to fix catch up. But of course, we still want to keep we still want to be able to keep our, we still want to have archive nodes running that can keep track of, can store the blockchain.
Sure.
And of course, storage is cheap these days. Like, I know 1 terabyte, it sounds like a lot for an individual person, but for a company, in a proper size company, they're gonna have like a petabyte of data stored. So
I think the difference is that on archives, maybe you don't have to spend as much because you can use it as a hard drive space, like HDD. But if you use Relay, I think
you're right.
you need like SSD. Yeah, so that's difference.
That's a good point. Yeah. So what I would imagine is that we could see sharding, data sharding. I would love to see that.
Yeah, the vaulting thing about Algorand was interesting.
Yes, Algorand Vault, but definitely data sharding. So, and then you would pay for that, and then maybe do this data availability sampling to make sure that you still have that data, and maybe so we'll see. Like maybe that's something we will see people do. Like to be like, well, I want to help pay for Algorand to keep these archive nodes, and to decentralize how to do that. So let's create a smart contract where people can prove against smart contract that they're keeping the storage of Algorand archive, and then they could do the pairing checks, the KZG commitment, all these things that we talked about. So they would have Algorand beats. Yeah. So there is that. We could see that. Maybe we could see something. Maybe we will see like almost like an L2, like a second layer on the blockchain, where it's kind of like proof of time and space, or whatever they call it, or space, where you're proving that I think that's what to use. And was it Filecoin to do that, or
probably I
think maybe also Clio? I forgot. Anyway, so maybe that would be something interesting to look into to incentivize archive nodes. So there's that, and then of course there's the aspect of, well, do we need like what if we need, I'm really I really want, what I would really want is this kind of 2-tier relay nodes, right? Where you can have, instead of paying, instead of let's say paying, because now it's from the foundation, and then it's eventually going to be from the transaction fees, right? Paying these 100 relay nodes. Maybe we should only be paying like 10 super blocks, like these 10 super nodes, right, in the whole world, and then we have maybe 1,000 smaller relay nodes that are used to kind of gossip, like, so you can kind of get this high speed network highway if you want to, so you can pay extra, or to fund these super fast relay nodes, or you can kind of get the super cheap fee, but then you have to expect your transaction to it has to
to be gossiped slower.
It has to be gossiped throughout the network across the whole world, and then eventually it has to be eventually, like it has to reach enough, like your transaction when you give it, like has to be gossiped through the network and then be included in enough participation nodes, mempools, whatever you call it, not mempool, but you can whatever you call it, transaction, like pools of where that they will eventually include in their own blocks, and so that could take a little bit of time, but maybe that's because right now I have seen people do complain. I mean, other chains are saying the Algorand cheats because of course you can.
Yeah, you have relays, so you're cheating, you're cheating speed, because the Justin Bounce raised this critic because it says yes, Algorand scales, but it scales because communication layer is bottlenecked to another layer, like it's not inside the same nodes. Well, I think many chains already do this. I think there's some other chains. I think Near, maybe, I don't remember, but other chains have these like smaller nodes and bigger nodes, and bigger nodes and beefier nodes like cheats because you have them managing the most of the traffic. And so the key difference in Algorand is that I think it's actually the positive part of Algorand is that when you consider blockchain as a uncensorable layer, like you have the main point is the consensus layer, but if you want full uncensorability, you also have to have a permissionless communication layer, because Relay could filter out transaction from the like, yes, you can have anyone participating in the consensus, so there's no like neither a minimal, like a high minimal requirement, or some sort of, I don't know, harder requirement or anything else. Okay, but like on the communication layer, I think that the main point that they're doing, actually, I think that's what they're focusing on, because it's been raised a lot, this issue, like, hey, Algorand, are you fully permissionless? You can explain that, yes, it's not censorable, because yes, there's permissioned communication layer, but it's not like they're going to be censored, because you relay transaction to 4 to 5 different relays, and so it's very hard to attack this communication layer. But still, when you want to talk about it, yeah, it's a bit like, yeah, but it's you get always, yes, it's permission thing. So it's not the greatest. But yes, what you were saying, actually, I want to also quote, like, in Algorand Italy, a Telegram group where I was talking with Massimo, like, he was one of the members, about Algorand scalability, and here's the good point: is Algorand is extremely scalable to the future, like upscaling, but not downscaling.
What do they
like
mean?
Algorand will need downscaling, like because right now you have this extremely performant infrastructure that is not as used as it should be. Like, you have fewer transactions, but you have like a still beefy nodes, like relays that are running and are expensive. So to have like a future-proof chain, maybe it will need to implement some sort of downscaling feature where, depending on the usage, there's like a direct proportionality of cost to keep up relays or participation. Like if there is like what you were saying with 10 beefy nodes that do like a super fast transaction, and then you have like smaller. So the future-proof thing will be to have basically this set of relays being easily like took up and took down depending on the usage, like on the requests.
Yeah, I mean, yeah, it depends. Like, the thing is, like, because you have beefiness, which is one aspect of it. And you also have location-wise. So what you do, I mean, obviously, like, if you had one giant relay node, that would be like the fastest, because then it would just it would just accept everything, and then it would just do checks and stuff, right? And so like, when we say like scaling up Algorand, like, it doesn't necessarily have to mean that, oh, you need more relay nodes, right? It can also mean fewer relay nodes. But then you have the aspect of, like, you know, location, right? Because you need enough relay nodes to cover the globe, right? And then you want size on them so that they can be fast. But then you also want, of course, enough to get decentralization. So that was kind of my idea, that you would you could have few. But then, of course, like these, I mean, whoever is running the relay nodes can choose themselves how much they want to spend. I mean, and then you would want to, you know, how much resources they want to bring up. And definitely, like, what you would want is you would have a you know, if you have a way of paying transaction fees, you want to you want a way to reward relay nodes for being good, you know, for doing their work, because they are paying costs. Like, they're not, it's not like participation node where, you know, oh, I have 1 billion algos and then you have 1 million algos. Oh, I deserve, you know, 1,000 more in rewards. It's not like that. You know, the work doesn't scale for participation nodes, because everyone's always, you know, creating blocks with a VRF. But for relay nodes, it is completely dependent. And so you would want a way that if a relay node is slow, then it gets punished, and so it needs to kind of, you know, if there's enough activity, then it needs to be able to scale up with that activity. And so and because otherwise it's going to perform badly, and if it performs badly, it's going to lose out on some fees. And so that way, what you would do is you would have, like, you know, you could do, it's called vertical scaling, right? Or horizontal, I don't know, vertical scaling, presumably.
To beef up the beef,
exactly, beef. Because and then you just have that, and then you're just happy because it's enough, or maybe 20 nodes. I don't know, but I think 100 nodes is probably too many. Like,
But
100 nodes, if it's many, like it's not enough. If you only have these beefy nodes and 100 nodes, for me, it's not enough. You want more. But then if you have a mix of small and big nodes, then you could have much fewer small big nodes that are gonna get a bigger chunk of the price of the fees, right? And then maybe right. And then you could have all these other nodes that are gonna just be doing free stuff, like this free labor. Like,
but actually, does because you said that the fewer the relay nodes, the faster it is, right?
I think so.
But isn't it the opposite? Because it's not consensus. Like the relay nodes don't have to communicate to each other; just have to communicate to participation nodes. So the more you have, the easier they reach out to participation nodes. So
yeah, but then you have more friction between the relay nodes. So the relay nodes themselves are talking to each other, and that creates friction.
do they talk to each other? Oh, okay.
Yeah, because they have to, right? Because a relay node.
I thought it was like participation to relay to participation, not like.
I don't think so. I think it's like participation role. I think
relay
they do both, right? Because otherwise, like, how would they talk? Like,
you need to relay to relay.
And there's a relay node in Africa, like.
But you don't need to. You don't need those relay to reach consensus. You need participation to reach consensus. Even if there are like more of them, you're just going to wait. I don't know if I'm confusing myself. Because they just have to. Okay, they have to gossip to each other to gossip the block. Okay, the transaction. But they don't have to like gossip back. So I think.
Because it's not just about blocks, right? It's not just about blocks. It's about
transactions
as well.
Yeah.
So then you want to gossip to everyone the transactions so that someone is going to win at some point, right? But you don't know where they're going to win, where the person who's going to win is. So they need to be given all the transactions, and then from there, producing their blocks. And so, yeah, at least from I'm not an expert in these systems.
No, because I think I don't. Yeah, I'm not sure about this because I only remember reading something about from Patrick. I don't know if you know Patrick from
Bennett.
Yes.
NFT domains.
Yes, NFT domains, and he was talking about this. So I'm not sure because I'm not fully sure this is what he said, but yes, he was talking about the thing that since you also increase the fan out, you also reduce the. No, well, actually, he was talking about the more relays, and that is not going to be like proportionally direct to the speed of the network. Like you have many relays, so speed goes down, and you have fewer relays, and the speed goes up. So
yes, but then you also have the number of connections, right? So that's also maybe something.
The number of connections, yes. If you have if you increase the fan out of the participation nodes to different relays, so at this point, relays don't have to gossip to each other because this participation node is already gossiping to more relays, and this makes it faster. Like you can have you can account for 10 times the relays if you just increase a bit of the fan out.
Yeah, so there's some kind of optimization you have to do there, where you're looking at number of.
I don't want to say that he said this because I don't remember, but he's going to what it is saying. He invented things now, but
there's some kind of optimization there between right, like where geographic location, because we want to be as geographically possible, and you want as many as possible for decentralization, but same time, so we need more nodes to cover the globe. Yeah, that's going to create. But then there's going to be at some point it's going to be too many real nodes because the it's not going to be worth it unless you care about decentralization, because it's going to add more of these kind of friction. Because they all need to talk to each other and evaluate each other. See, did I already hear about this? Did I already see this transaction before you use it to me? Oh, well, then I don't need to care about it. Or no, I haven't seen it already, so then good, I'll pass it on. And then, but maybe the other really know has already seen it, and then they'll be like, I don't care about this because I already seen it. So you have this extra competition that is taking place because there's more. It's like
I think that's.
Yeah. So I don't know. I guess so. I think that's where we need to look at. For me, at least, that's what I'm interested. I'm not too concerned about L2s I do care about
Yes.
interoperability. I think that's very big, but that's not really LTU stuff. But yeah, the bridges, Oracle's super interesting. And yeah, of course, looking at relay nodes, looking at archive nodes, how we can look into archiving, and definitely, yeah, and Algorand Vol, all these things. So that's what I'm thinking. The next is just the end. And I don't know. Of course, the question is like what we're going to talk about next.
Next. There were the same topics that we were discussing last time, like ZK-SNARKs, state proofs.
Yeah, we could look into those, but of course, the thing about those is they're also very advanced, and so
very advanced. Yes.
What we could do is we could look at something very limited, and then not have like a huge gap.
Or maybe we could just stick a bit on this topic about blockchain and not. I don't know. It depends if we want to go back to cryptography or stick a bit on this more architecture infrastructure side.
I mean, like last time we talked about a lot of those. I mean, there are a lot of options for us. Just like
yes.
Go deep into cryptography, just like post-quantum stuff. There was MPC stuff, right? And what friends doing with like, can a blockchain keep a secret and all these things? And then it's also the casino stuff I was looking into, or I'm still looking into now and then. I just so full time, and then of course there's some ZK stuff, and there's also the example that Barnji made for how for ZK-SNARKs on Algorand, how to deploy it. We could look into that, talk about that.
Yeah, I actually want to ask you, maybe like for some weeks when I have to do my project, I want to go over what his work was like on the repo to understand better how. That would be interesting because actually to understand how do you develop ZK-SNARK on Algorand.
Yeah, that's something we can look into. Of course, this topic was given by Naruhito. And he or she didn't show up, or like so.
We should. I thought since we have like a very lengthy video recording, we should. I don't know. Maybe I'll try to help you. Once you upload it, I'll try to take track of the parts of this video so we can easily.
Thank you. Yeah.
Check it back. Yeah. We talk like 4 hours now.
Yeah,
it was very interesting.
Actually. Yeah. So. I mean, I'll just edit out some parts. I'll edit out. I'll edit out some parts, and then. Actually, I'll just stop recording now.
It's going to.
Yeah, this is the end. This is the end. Thanks for participating, and I'll see you next time.
See ya.